start to kick off today's session. So hello, everyone. Welcome to today's session. And my name is Nina, and I'm a part of the storytelling team at RISE-MICCAI. And I will be your moderator for the first part of today's program. So it's really my pleasure to introduce you, Dr. Islam Rakat, for the first part of our today's program. Dr. Islam Rakat is the director of the Brain and Signal Research and Analysis Lab and an associate professor at Imperial College London. And together with her team, she conducted more than 90 cutting-edge research projects in AI and healthcare with a sharp focus on brain image and neuroscience. And she's also a very passionate advocate of equity, inclusiveness, and diversity in research. She is the former president of the Women in MICCAI and also the co-founder and then the previous RISE-MICCAI president. So without further ado, let's welcome Dr. Islam Rakat, and then, I'll hand it over to you.
Thank you. Thank you, Nina, for the lovely introduction. So I'm really excited actually to be here today. I know there are so many of you who are joining in person and also online. So I'm also the general co-chair of MICCAI 2026. So I'm really excited about receiving your submissions, your paper submissions to the future edition of MICCAI, which will take place in Abu Dhabi. And so today I'm going to teach you a little bit about design thinking and how can you come up with new ideas for your research projects. So feel free to write your questions. And then this session will be slightly interactive. I don't want to just, kind of talk for hours and not hear from you. So I know it's a webinar, but I will allow you to kind of express your mind through a website called Slido. So make sure you have your kind of browser ready to go. Okay, cool. So as all of you guys know, AI, or which stands for, of course, artificial intelligence, is a very hot topic these days. So there are so many research papers that are published around AI to solve problems in healthcare and education, in business. So you can see all these papers published around different topics, leveraging AI tools and designing new AI solutions to tackle hard problems across multidisciplinary fields, okay? So for example, here, the role of AI in achieving sustainable development, transfer learning for scalability of, like neural quantum networks, which means in quantum computing. So also, we are hoping that the future will be super intelligent with this kind of AI revolution. And as you guys can see in this report, which was published years back by the Royal Society in the UK, that they have envisioned that machine learning will drive advances in healthcare, teaching, transport, and more, supporting public services, boosting the economy. So there is a lot of good also for, a lot of good things to do for the society, to benefit the society. So and this eventually has led very recently to Nobel Prizes being awarded to leaders or in the field of AI, particularly the godfather of AI, Geoffrey Hinton. And so AI is a scientific breakthrough that was awarded a Nobel Prize. Yeah. So there's a lot of things that we can solve with AI, but maybe you guys don't know where to start. So I'll give you a few tips during this lecture or this talk. So as you guys know, also AI can be used to solve really hard and highly abstract problems, okay? For example, we envision that AI will be used to define the next generation theorem provers, which means prove a theorem that was hard to prove for maybe decades, right? Or new theorem, right? So a mathematician named Gowers has said that he thinks computers will be able to out-reason mathematicians by 2099. And this statement basically was quoted before the era of large language models like GPT, Gemini, Claude, Perplexity, you have Grok, all these kind of, LLM models that are available publicly. And I do believe that this breakthrough will happen way before 2099. And I hope that many of you will contribute to this with your research and also your smart brains. So in his quotation from the University of Cambridge, he mentioned that machines will learn how to do their own prompts. So for now, for example, as users, we enter our prompts into, like an API, like an LLM application or app website. And then by typing in our prompts, you interact, you ask something to GPT, you have the response, etc. But in the future, we anticipate or envision that a machine will know how to self-prompt, like how to actually ask the best questions and answer them at the same time, okay? So basically, I just wanted to give you a flavor of this whole field of AI that is revolutionizing all sciences, humanities, all sectors. Using AI, we can learn how to generate anything from anything, literally, as long, of course, you have some rationale and logic behind it. So you don't want to kind of randomly do stuff. So the idea here is quite simple. You have an input data. It could be an image, a video, text, could be any kind of data. And you input it, you feed it into your AI model, and this model will produce something you desire, which is your desired output. Like, for example, if I give an AI model an image of an MRI of a patient, it will enable me to predict whether the patient has a particular neurological disorder or they are healthy. Okay, so it's a classification problem here. So there are so many things. You just need to define your X and you define your Y. Once you have your X data and your Y, you can work on designing that, the box inside, which is the AI model. So now, I used GPT to generate all this Wimpy Kid illustrations, which was so fun yesterday, for me. So this is a very simple or cute illustration of the idea of crisis. So AI-dia, which means, how to find an idea in AI. And you have a crisis, so you don't know how to come up with new AI models. How would you go about that? So you have loads of papers. You may be a PhD student, a master's student, or a researcher, professor, doesn't matter. Or maybe like somebody who just very curious and wants to learn about this field. So you can't find new ideas. So you go over all these papers and you really struggle to come up with new ideas. And this is what we're gonna tackle today, okay? So the answer here is, okay, so the first question, let's ask questions. So this is a very cute illustration, as I said, produced by GPT. So how do I come up with new ideas? I don't know how to design new AI models, but you can see there are so many mistakes, by the way, in the comic. So visually speaking, the GPT is still not performing very well, but I do believe it will get better in the future. So there are lots of visual inconsistencies, like the glasses are disappearing, reappearing. It's not the same person. So anyway, so how do I come up with new ideas? I don't know how to design new AI models. So the guy says, oh, the literature is overwhelming, right? There are lots of papers coming out every single day. So the advice here that the teacher is giving, stay up to date on what others are doing. So, okay, so probably it's not solving the problem because the guy is reading all recent papers and he's up to date, but not very easy, right? Like to find new ideas. So I think the dialogue that GPT produced was not the best, but anyways, I tried to prompt it better to give you better results. I'll show you in a few minutes. So yeah, so stay up to date and look for gaps or limitations. So this is a key thing here, okay? I think this is a very important thing. Where to start for you to be able to come up with new ideas is to find weaknesses or limitations of existing, solutions of, recently published papers. Yeah, so I'll give you some, strategies in a bit. So yeah, so this was, a very quick sneak peek into what GPT has produced. And before we get into the design thinking rules, so I'm going to teach you 6 rules today and 3 strategies. So usually, guys, this course, I offer it over 4 to 7 weeks. So it's a long design thinking course, but I've tried to simplify it and kind of give you the basics. And then from the basics, you can then extend your knowledge and, learn by yourself, okay? So please go to slido.com. So this is a website. So you can type in slido.com and then you have a code to write. So the code here, you don't need to sign up. You do not need to log in. You just need to write the code, which is RISE-25DT. And once you do that, you can join the, basically, you'll be able to take the survey in a bit, okay? So we have Nadia, you have a question? If you do have a question, you can type it in. I should be able to see it. Yeah, so it's quite simple. Yeah, Nina? Sorry, I think, yeah, that was a mistake. Okay, guys, so slido.com, just type in the code and you can join as a participant, okay? So using this code that I showed here, okay? The RISE-25DT. So now I'm going to go to Slido and I'll show you the results. So that's a good thing. So the survey is on. I see 33 people actually typing in quickly. So it's a quick survey, should not take more than 2 minutes or maximum, okay? Ticking boxes, and I'll show you the results in a second so you can see, what the whole distribution of the attendees here and their responses. Cool, very good. So 1 more minute and or 2 more minutes, and then I will close the survey, the DT survey. As I said, you don't need to sign up, and it's fully anonymous. Okay, so which means I don't know who you are. Feel free to tick the boxes the way you want. And use this code to join as a participant. All right. And I think I'm going to sit down because I'm going to be writing in a bit. Please, guys, make sure you join the survey. It has very simple questions. I just want to know, how do you feel about design thinking in general and coming up with new ideas, new models? All right, so I'm going to share in real time the answers, but make sure that you guys go to, as I said, again, the slido.com, the website here, and this is the code to enter. Okay, RISE-25DT, and maybe you can broadcast it again, Nina? Yeah. So I think I can write to everyone, so. All right, cool. So let me stop my screen sharing and show you the responses here, which is quite cool. So this is what we're having right now in real time. So 119 votes. And these are the answers. So we have lots of people from, different parts of the world. That's so wonderful. That is really nice. Okay, cool. And now, how easy is it for you to come up with new ideas? Difficult? So hopefully you'll learn a few tricks. It will be easier after this very short session. Okay, quickly. So I'm going to go over this also. How often do you actively try to improve or rethink existing solutions? Often. So that's not always. It means often. Okay, so try to engage, but not fully engaged. Next question. Have you ever designed or contributed to an AI solution or project? So 60% say yes. 20%, about 20%. I think like the 40 is like partially or maybe not. So it's a great opportunity for you to learn today then. How often do you think critically about the limitations of existing AI models? So, well, 50% say often, sometimes 25%. So it's like, I think this cohort like 50-50. Okay, so we need more engagement, thinking about limitations. Okay, have you ever tried to improve an AI model or suggest a better approach based on your analysis? So 50% said yes, so that's good. And the others, like they are kind of no or partially, or I don't know how. And word cloud, in one or two words, what is the biggest challenge you face to come up with new ideas? And I think here, there's a frequency here. I think knowledge, lack of knowledge or domain expertise, not knowing, basically, which is really a fundamental factor or challenge, I would say. Time, how to innovate. And there are like, okay, different things here. Okay, cool. So great. Thank you for completing this this survey. I think I have an idea about where you are, guys. And now we can, I just stop this so we can get to the crux of this presentation today. I'm going to show you other examples on PPT later. Okay, cool. So before that, quickly, so let me get back to my PPT. Actually, it's good to do that just to introduce this part. Okay, so this is the strategy that I will go over in a bit. So how do we come up with new ideas? You, of course, need to read many papers, but you may not have a clue about how to come up with new ideas, despite the fact that you're reading a lot of papers. So here, how do you even begin? Yeah, so I think all of you have the writer's block, right? Like, which is the designer block here. Like, you don't know how to begin. Everything has already been done. So this is the impression that many students have, guys. Many students think that they come to me and say, like, I don't know how to come up with a new idea, right? I think everything has been solved already. So what can I invent after the transformers or after these attention networks, right? So then start by picking a narrow problem. So the idea is like, first thing, maybe you can take notes. So you need to really narrow down your problem. And then once you do that, you then can study 3 to 5 papers trying to solve that problem. So basically 3 to 5 papers, and try to identify what doesn't work in the paper, where the paper is failing. And usually, where do you find these limitations? In the discussion section of the paper or the conclusion sections, right? So if you read the discussion carefully and the conclusion, you will be able to easily spot out at least the explicit limitations of the paper. And then you need to think about, how can I fix them? How can I rethink this problem and fix these limitations? So that would be what we call your research gap. That's your starting point. And once you find that, then you will use design thinking techniques to solve the problem. So find your gap, design think. And what I'm going to talk about now is to actually how to design think and how to find your own ideas. So the first thing, the first rule before I get into that is to actually learn how to challenge yourself. So I want to tell each one of you guys, I know that many of you have said that I, often think about how these limitations, I often try to solve these hard problems. So the real problem is that, number one, we are not challenging our brains and ourselves enough, okay? So usually what happens when you start doing research, you are at the beginning of this beautiful curve. So it's kind of growing somehow exponentially. So you see that growth. You're happy because you see some results. You're trying to implement some existing codes. You're just using what is there, trying to recode a unit, a CNN, an MLP, a transformer, and it's easy, okay? Now, once you want to come up with your new ideas, you hit what we call the plateau. And the plateau is very common for any learner trajectory. Like this is a very common flat area that you need to hit. And what happens here, unfortunately, many students, many learners, they drop out. They give up. They say, I've been practicing and practicing and practicing and practicing, and nothing is happening, right? I can't get new ideas. I can't progress, right? So they feel stuck because they are in this area in their learning curve. And for you to be able to get through that, you need to keep going. So what is happening, actually, you may not feel the immediate reward, okay? You may not see the immediate results in front of your eyes, but your brain is working. Every day you're reading papers. Every day you're using, applying the design thinking techniques I'm going to share with you in a bit. You're engaging your brain. You're trying to think about it, even if you feel that, I don't know what I'm thinking. That is totally fine. So as long as you engage your brain, you're constantly thinking, engaging with these papers about, I don't know, LLMs, segmentation networks, whatever topic you're working on, and recent papers, trying to kind of read recent papers, recent trends. So you are progressing, even if you don't see any results. So what happens at some point, this will grow back exponentially. And that's how you thrive, okay? But first you need to persevere. So, you need to persevere through the plateau, and you need to keep at it, and keep at it very seriously and very hardly and very smartly, okay? So you got this. You can come up with new ideas. You can say to yourself, I will work hard to improve my creative design thinking. And today I'm going to share the tools with you. And here we go. Rule number 2. So first rule is to challenge yourself, to really not give up and keep a very strong discipline. Rule number 2 is to master the 3 B's. So this is, actually a book I'm writing right now on design thinking. So I'll give you a sneak peek towards the very end of this talk. So the 3 techniques, the first one is called blending. So there are 3 B's. The first B bends. The second B breaks. And the third B blends. So these are 3 simple design thinking techniques. I can spend hours on each, but I'm going to summarize them compactly for you to understand the basics, and you can easily apply them, okay? Cool. So before we get into that, we're going to get into that. So that's the right moment right now. I've been postponing this. So let's look at my, switch to my iPad. And yeah, so basically, guys, we have 3 design thinking techniques, as I mentioned. Actually, there are more. There are 7, but I'm going to just talk about 3 because we don't have time today. And actually, this is good timing. So we can start with the first one. So what's the definition of the bending technique? I'm bending. So bending means to modify or bend one or several components, blocks, it could be steps of an existing solution or framework, okay? So for example, you take, it could be, like this pipeline. So you have a, let's say, an image here of a tree. That's the input X. Your Y is the segmented image. So you want to color it. You want the algorithm to put 1 for the tree and 0 for the rest. So that's a segmentation algorithm. Okay, so you want to segment. And your simple AI model here would have perhaps many blocks, but I'm going to give you a simple example. So let's say you have a UNet here. So a UNet has an encoder network, okay, and a decoder network. All right. So basically what it does, it feeds in this image. It learns how to project this image, which has n. So here it's this x. If we call this image x and we vectorize it, so we have n by n, so it's n squared. So it takes a vector of dimension n squared. For example, I'm just saying, okay, so, and then and then you move it through this encoder network. So in 2D, you don't need to vectorize. I'm not sure if you guys are familiar with different deep learning models and different architectures, but because some of you may not be familiar, so I'm trying to simplify. So basically, the key idea, whether you feed in the whole image as 2D or you vectorize it, you turn it into a vector, you want to project it into what we call a latent space. And this in latent space, you are simply encoding, so that's why it's called an encoder. You're encoding this image into a bunch of numbers like 0.2, 0.5, 1.6, etc. So magically, this magic vector right here that has maybe, let's call it Z, that belongs to our D prime, okay, it has D prime, has 3 numbers here, 1, 2, 3. You feed it into a decoder network, and then once you feed this vector into a decoder network, it will generate this image for you, okay? So somehow we have learned how to transform or encode this image into a new space, and from this new space where we have only a very compact representation, we can create the segmentation of this image. So this is a principle of majority of deep learning models, projecting into small, a very low dimensional space, and from there you kind of recreate whatever you want, your Y, okay? So the UNet here, for example, it's a very simple model, could be any kind of deep learning model, but if I want to bend it, so let's say I will add some attention mechanism. So I will, for example, when I do this learning of these, values right here, I will pay attention to some areas that are very important. So maybe this area is important for my segmentation because it's actually a tree. The trunk is important. This is a trunk. So I want to pay attention to these guys. Like I really want to kind of pay attention to the most important part in the image. And then if I learn how to pay attention to these parts, I can maybe segment better. So my segmentation will be of better quality. So this is sort of called bending because I took one simple component and I changed it in the whole architecture. So remember, I modify or change a simple component by adding a few things, right? So this is what we call bending. So you take an existing pipeline and you change that. For example, I'm going to give you a very simple example. So let's say in an algorithm, you're using clustering, okay? So there is a pipeline right here. So let's say, oops, okay, so let's take another image. So the same image. So we have a tree and we want to segment the tree, okay? So that's my Y, that's my input, and this is, here I have a clustering algorithm, okay? So I'm just going to do clustering. So I'm going to cluster pixels which have the same color. So here, this is, maybe the colors that I have here. I'm going to do all green for simplicity. But what is happening here that I'm trying to find the green ones, put them together, right? And the other ones that are white, I put them together, the background. This is the background of the image. So background, it means all these guys are here, okay? For example, okay? So, so in this example, what we're actually doing, we're using k-means. Let's say I'm using k-means, and I can easily cluster because the data looks like this, okay? So it's separable. The distribution of the data on this space are what we call a manifold, okay? It is separable. It's beautiful. Like you can just draw a circle and, cluster it. However, if you have a shape like this, what happens here? The shape is fully nonlinear. The data is following something like that looks like this, right? So then you cannot use the original clustering. So you need to do some banding. So k-means I'm gonna band it or change it with another clustering algorithm. And for example, here I use spectral clustering because spectral clustering enables me to capture fully nonlinear shapes of the data distribution, which means the distribution of all these pixels may be like this. So maybe the tree is right here and the background is right here. Okay, so then spectral clustering will give me better results. So bending, basically what it means, guys, if you have a full network with so many components, you take one component, one block, and you change it. Okay, so I'll give you an example in a bit, okay? So the second technique is actually, the first one is incremental. So bending usually, well, it depends, but you're changing a component or two in existing framework. So you download a code, you say, for example, I'm using this type of convolution. I'm going to change it with attention-based convolution. I'm using this type of clustering. I'm going to use another type of clustering. But it depends. Sometimes it could be very limited. Other times, if you say, well, I'm going to change it with a new way of clustering that's not there, then it's a bit more challenging. But let's keep it simple for now. Let's say modify or bend slightly. Okay, so it's not really creative, but it can improve the results. Okay, so if you do segmentation, you can have better segmentation using the bend technique. Okay. So the second one quickly is breaking. So breaking is actually very simple, guys. And I really like this technique. I've used it in so many of my projects at the Bosira Lab. Many students use this technique. And also we have the third technique, which is blending, which is really kind of innovative. So I'll show you an example in a bit that uses both techniques for coming up with new ideas. Okay. So what is breaking? Breaking is decomposing. So you decompose a concept, an idea, a component. It could be anything, okay? It could be a component in a network, like an attention module. It could be a super resolution module. It could be an explainable module, a reasoning-based module, a segmentation module, a classification module, for example. It could be a simple idea, like, the idea of clustering, the idea of, self-supervised learning, the idea of, super resolving images, image super resolution. So it could be anything. You take one thing, component, concept, idea, step, and you break it. So the breaking goes like this, guys. Okay, so you break it into different parts. And basically, when you break, you have the original component, the problem, right? And it is divided into either two or more. Okay, so it goes in this way. This is how the logic flows. So you have an origin, like an original seed, and then you have the multiple, I would say ramifications from that seed. Okay, so you're breaking a problem into part A and part B, and this is the problem P. Okay, so it's quite simple. So you need to break it down. There are two ways of doing the breaking in design thinking, independently or dependently. Okay, so I'll show you these two techniques. The first one is independent breaking. So dependent breaking. So the dependent breaking, it means when you break a problem into multiple steps, they are dependent. So one step depends. So step one here. So let's say I have my X. I feed it into a learning module called F, a function F of X. And then after F, I feed it. So let's say this is a network that does, for example, denoising. So it denoises the image because I put an image and it has a lot of noise. So first I denoise, I get F of X. F of X is the output of this learning module. So my F of X here, let me just remove this, guys, because I'm going to give you. My F of X here is denoised image. Okay. And then I do a segmenter here. So S of F of X. So let's call this an intermediate variable omega. Okay. So S of omega. So here, this is a segmentation module. Okay. And this segmentation module at the end, it will give me my Y. So my Y here would be the segmented tree. So why I did this breaking in a sequential way. So I did this breaking in a sequential way because first I needed to remove the noise to make it easier for the segmentation module to see the tree, to find the tree, because the noise may be so disruptive, okay? So I broke down my original segmentation task. So this is the segmentation task into first basically a denoising step module, number one, and followed by a segmentation or pixel classification or image classification module here. And what we have two modules that are back to back. So they are dependent. So the results of this guy, the results of the segmentator or the segmentation module depends on the quality of the denoiser. Okay, so at the end, if I write down this y is equal to S of W or omega. Omega is actually S of F of X. So that And this is what we call a composition rule. So I'm composing, okay, two functions or two modules or two architectures or two models, whatever you call it, okay? So you can do so many things. By the way, guys, sequential breaking is the fundamental idea behind the whole field of deep learning. This is how deep learning works. Deep learning, you have different convolutions. You have X, you move it into convolution pooling, whatever. Then you do another layer of convolution. So you have layer 1, layer 2, layer 3, etc. So what you're learning is you learn how to compose functions. You know, f of 1 of x goes into the next one, f2, fl minus 1 until the last layer. So you are decomposing a whole mapping called f bar or average. You're decomposing it into multiple steps that are dependent, okay, codependent. The output of one goes in as an input, becomes the input of the next one until you get to the final result. So this concept, you can see it everywhere. And what I really want you to start doing is to see it everywhere. Because you see it in deep learning, you see it in all deep learning architectures, you have even in LLMs. So you're stacking things, you're putting things one after the other. And of course, guys, for you to be able to decompose this in the right order, so why I put denoising first, so there is a Y here, and Y segmentation second. So there should be a logic and reasoning behind this. And this is so important. And usually this is where the students get stuck. And they get stuck because that's what you mentioned at the end, lack of knowledge and lack of expertise. And how do you get this? You get this through the next rules I'll explain to you. Okay, so I think you understand the idea of breaking, sequential breaking. So you break into different steps. And now you have hierarchical breaking. So hierarchical breaking reminds you of what? If you've done some clustering, for example, it's hierarchical clustering, right? So you cluster into big blobs and then you subdivide into smaller ones. So you have, you know, a big cluster, which is the whole data here. And then you divide this into two. And then each you start by dividing into subclusters. So there is a hierarchy. There is, you know, a first, you know, division and then second, etc. So what happens here, this is similar to the chain of thought. Chain of thought, if you don't know what it is, you can read about it, that LLMs use to verify their logic. So they do step by step. And there are linear chains, by the way. So there is a linear chain like this, so which is dependent sequential. So this is simple sequential, what we have seen. But we have what we call a tree of thought. So a tree of thought. And this is in NLP. So tree of thought, it means you take an idea and you have multiple ways of answering that prompt, right? So this is the original prompt. I will generate many ways of, you know, getting to the final answer. And there is a hierarchy here. And what happens is that I have multiple pathways, okay? So I have pathway 1, oops. Okay, so let's do this smaller. So pathway 1, pathway 2, pathway 3, etc. So I'm traversing the tree and I'm hoping that I'm going to get the best results at the end. Okay, so this is hierarchical, you know, like breaking. So you're breaking one problem into sub-problems. And usually the last layer here will give you the best results. So that's one way. You can think about it differently. You can say, actually, it's the best, you know, pathway that crosses that tree. That is my solution. So your solution could be a pathway in the hierarchical breaking, like in the tree of thought for NLP. And it could be the final clusters, like here, hierarchical clustering with the dendrograms, which is the final cluster that you're going to get towards the very end, okay? So it depends on how you apply this principle. So a tree is a magical data structure. There are so many papers that are based on trees. If you just take the concept of a tree and any paper that is published, like GNN, like, you know, attention networks, like, I don't know, reasoning-based models, explainable models, interpretable models, segmentation, classification, whatever you name it. And you say, I'm going to try to use a tree in my project, you will see so many things, and you can use it in different ways, believe me. So that's where you need to think and engage and look at the same entity from different perspectives. So this is a skill you need to develop, which means I'm looking at the same object, the same structure, but I'm thinking about it differently. Okay, so keep that in mind. So anyway, so I think you understand what breaking is. I need to hurry up. So we have dependent hierarchical, dependent sequential, like deep learning models, like, segmentation models with different modules, building a hierarchy, and then the independent one. So independent breaking, it means you break an idea, okay, into multiple ideas. So idea 1, instance 1, 2, and 3, and then somehow you aggregate. So you aggregate here. So this reminds you of what, guys? Independent breaking. So let me give you an example. So if you have an SVM, support vector machine classifier. So we have a family of classifiers, okay? So we have multiple classifiers, simple machine learning classifiers. I'm not going to talk about deep learning. You have, for example, random forest. It's a classifier. You have Bayes classifier. So you have all these kind of, classifiers. So what you do is say, instead of, everybody is using these classifiers independently. But what if I try to break my classification problem? So I want to classify an image. So this image, the label is 0 for no tree and 1 for a tree. So if there is a tree, the output of the model should be 1, okay? So I will break down my classification model into different steps. So step 1, I will use, for example, model 1. I'll train model 2. I'll train model K. So I have K models. And each model will learn a particular, I would say hyperplane or particular classification line here between for the same data, okay? So something like this. So what happens here, you consider each model as an expert, but these guys have maybe complementary expertise. So that's the rationale. That's your thinking why. So all these guys may have pros and cons, but maybe when I put them together, I can generate something better. So I'm going to train them independently. So each one is independent. And then once I train the model, I'm going to get the parameters are model 1, tilde W2, tilde W3, WK. And I have all these models. And now what I can do, I can test, I can bring in a new a tree, whatever it looks like this, maybe, X tests. And I'm going to, test the model. So I'm going to get FW1 tilde X test and get a Y here. Okay. So this is Y1 by model 1 prediction. So tilde. And then Y2 and then YK. So what happens, I'm going to get different predictions by all these models. And at some point, I want to aggregate or combine the information by all of these. So if this guy says it's a tree, it's not a tree, I'm going to do a majority vote and say, oh, it's a 1, okay? So the rationale behind independent breaking is actually to aggregate, to generate different pathways of thinking or solving the problem and then combining them together at some point, okay? So, but they're not cross-communicating. That's why it's called independent. Independent because there is no exchange during the learning or during the training between these. If there was an exchange, then they become codependent or dependent, then we have sequential or hierarchical, okay? You can have other types, of course, but these are the simplest ones. Okay, so we spoke about the breaking, how you break a problem into different problems in different ways, whether sequentially by, kind of defining different steps that are dependent or independent. And the last one here that we're going to talk about is the blending. So blending is basically when you take two concepts that have never been put together and you put them together for the first time. So you blend, merge, so blend, merge, fuse, integrate two or more disparate ideas. So you take, for example, let's say, I'm going to give you an example. You take super resolution and you take the word graph here, and you say, okay, super resolution in the whole literature has always been, applied to images, but I want to apply it to graph. How can I do that? So these two terms have never been blended together, have never been put together, combined together. So they're completely different. And usually blending, guys, is the easiest way to get results and define new fields, because you can prime a new research field, because you are the first to, for example, use physics inspired differential equations to guide the neural network training. You are the first to do, for example, generative brain connectivity, trying to generate brain connectomes using quantum states. I'm just saying things here. By the way, all these things could be implemented. I'm not sure there's something like that. But yeah, so if you take two things and you put them together for the first time, you would be the first to start a whole field. Okay, so and this is usually the easiest way to innovate, because you have less benchmarks and less comparison. So I'm going to give you, I don't think I have time to go over this case study because we're running out of time. But yeah, so I'm going to share this with you. So this is actually a paper published in IPMI by my former PhD student. It was selected for oral presentation, and we used two design thinking techniques to come up with the main idea of the paper. So let me show you basically what the state-of-the-art solutions at the time. So at the time, what we want to do is we have a brain network here. So I'll try to go quickly. I hope I can get extra 5 minutes because we started 5 minutes late. So yeah, so here we have a brain network. So this is a brain network. It means it's a matrix, it's an adjacency matrix, okay? It's adjacency matrix of a graph. So you have region I, region J, and the connectivity between them over here. So this is the brain. I have region I in my brain, like my frontal lobe, my occipital lobe, and the connection between them, it's the value of this edge. So I'm not going to give you feedback how this works, but you can think about it as like this, okay? So 0.8. That's a matrix. And usually when you want to generate a target matrix, like for example, I want to predict how my brain looks at time point t+1 from t, okay? Or if I have a particular modality, let's say modality 1, and I want to predict modality 2. So these are completely different modalities. So for example, this edge here looks at structure, and the same edge here between I and J looks at function. So this is what we call a cross modality generation problem. So previously, because these are two different modalities, they have different distributions, okay? So this is the first distribution, the source domain and the target. And you guys can see there is a shift between distribution. So we found a problem here. The problem is like the existing solutions do not solve the shift, okay? So we proposed basically a new solution that allows us, number one, so the first thing here, number one is to change the dimensionality of the target graph, because nobody has done graph super resolution, making graphs bigger of the brain. And number two, we fix the domain alignment. So we make sure that the target and the source are aligned during our training. So both distributions become aligned. Of course, there is a lot about this. So you can read the paper if you want to know why we're doing that. What's the intuition? But as I said, first, guys, to recap quickly, you need to find challenges, okay, gaps and limitations that are unsolved. So these challenges should not have been solved. You are the first to solve them. So existing solutions do not solve these problems. Like, for us, shifting the resolution, number one, okay, so changing the resolution here, which is, generating graphs while allowing for a resolution shift between the source and the target domains. And the second gap is super resolving, which means increasing the resolution of the target graph, so generating larger matrices. So we were the first to tackle these two problems. And yeah, so there is basically breaking here. So we broke our graph super resolution problem into two parts, cross-domain. First, an aligner block. So there is a block A that is here. And second, a block that solves the challenge of super resolution. So the first one solves the challenge of alignment. The second one does the super resolution, which is, the graph generation, okay? So this is block B, and this is breaking, sequential breaking, A, then B. Now, what we did also, we did breaking. So breaking, it means, blending. So we took a graph, we took super resolution, we took cross-domain, multimodality, and we put them all together in one framework. So we did what we call blending, okay? So that's how we applied these techniques to get new ideas. But the first thing, find your challenges, think about how to use design thinking techniques and which one to use to design your solution. This is my solution. How would I go about fixing the resolution shift, okay, going from R to R prime, and the domain shift? I have two shifts here to fix, and I need to design the architectures in a way that they will fix this. Okay, so breaking usually works, but then you need to, of course, use the what's, like it maybe existing methods. So at the time, GANs were popular, so we used GANs. So we did not really modify this. GCNs were popular, so we used GCNs. Okay, but the whole idea is still novel, and the way we engineered it is fully novel. Okay, cool. So now one thing, you need to have the right hypothesis or rationale. So what does that mean? It means basically what I just expressed. Like you say that we hypothesize or assume that graph neural networks will enable us to kind of design our resolution shift. So I know that, I hypothesize that GNNs are good at this. And I hypothesize that if I align the distribution, I will get basically better super resolution. I will improve the super resolved graph. So this is an assumption I'm making, a hypothesis, a research hypothesis I'm making. I need to evaluate, okay? Then how am I going to actually turn this into something real? I need to design my model, my blocks, my, here Iman GraphNet, okay, the whole architecture. Cool. So that's that. I'm going to stop here and get back to my PPT to wrap up with some more advice and more tips for you guys. So remember the 3 Bs. So I bend, change one or few components. I break, independently, hierarchical, sequential, or independently. And then I blend. I take completely 2 different things and I try to kind of at least have some existing codes to modify to kind of get into defining the new space that I want to work in. Yeah, cool. So rule number 3, after the challenging yourself, the 3 Bs is to read actively. So it's so important, guys, that I think majority of you do not do that on a daily basis. If you are a researcher, if you are a PhD student, master, undergrad, I strongly, recommend that you read actively. What does that mean? It means first you skim the paper quickly to understand what the problem is, what the solution is, and then you read deeply. You try to find the hypotheses, the methodology, the assumptions. How did they design their experiments? Why they use these data sets? Why they use these evaluation measures? So usually what we do, we blindly use accuracy, sensitivity, specificity, all these things. We don't even question what we're doing, but we need to understand every single thing, because if you understand, then you are able to innovate. If you just use it as a black box, your brain will operate as a black box. You won't be able to innovate, yeah? So ask yourself, is this the only way that I could, I could have this problem that I'm reading about? Like, for example, when you read the paper Iman GraphNet, that one I showed you, you ask yourself, how can I solve it better, right? How can I, improve it further? What are the limitations of this architecture, right? It uses GANs. GANs are have a mode collapse. They are difficult to stabilize, right? Maybe diffusion model is better, but diffusion models are even noisier, right? Harder to train. So maybe I should come up with something better. So that's how you know. I'm citing these technical words because we need to learn. Otherwise, you won't get ideas, okay? So it's hard work. It's not easy. So rule number 4, quickly. So I'll wrap up in 5. So analyze smartly. So reading the papers, taking notes, analyzing figures, thinking, and basically asking yourself, how can I formalize or define the problem differently, maybe, or better? So maybe you guys do not have the answers. By the way, I'm going to share these slides on the website. So if you don't have an answer, it's totally fine. As I mentioned before, you hit the plateau. As long as you ask your brain questions, the brain will engage into thinking. Your subconscious mind will be thinking about the problem if you're really engaged. What does that mean? It means that even if I don't know how I'm going to solve it, I'm going to solve it. I remember when I started my postdoc, I spent 3-4 weeks thinking about the problem, like writing, scribbling things. I have no idea what I'm writing about. And then after reading many papers and connecting things, I got the idea, but I needed to struggle for 4 weeks to get just a simple idea. And that's normal, but I kept at it, okay? So you keep moving, persevere. So could the method be more general, more efficient? How can I make this method better? Maybe I don't want to improve the performance. I want to decrease the training time because it's costly, right? So there are so many questions you can ask related to problem statement, motivation, results, etc. So I'm going to skip this, but you'll have the slides to go over later, okay? So rule number 5, and this is the penultimate one. So spot design thinking technique. So from now on, how do you learn how to use the 3 B's, guys? Okay, by reading papers and saying, oh, was this blending? Was this breaking? How did I break the problem? Oh, this is interesting. This block is actually breaking. I can do something similar. So that's one way. So try, when you read papers, watch videos, try to identify the design thinking techniques. Which DT was used? Can I use another one to have a better solution? So they use, for example, bending. Bending is very incremental. They just change a few components. What if I introduce breaking here? I have a good intuition. The data is highly heterogeneous. It's not homogeneous. So what I'm going to do some clustering in the middle because that will disentangle the data, make it homogeneous, and then the model can learn better. For example, okay? So you need to have the right intuition, and intuition comes with reading. So the last one is practice design thinking. So weekly exercise. So you can read 2 state-of-the-art papers. One old paper is so good to go to the very old papers, maybe published even in the 90s, right? And use design thinking technique to combine ideas. So it's like a game. Sit down and try to play a game. Make it fun. Make it not just, I really need to get this paper out. I really need to get published. No, that's not why we're doing research. It's fun for and foremost, I would say. It is definitely useful and beneficial, so we're doing good things here. But yeah, so it should be a fun exercise, and you should do it daily. So that's how you improve, especially if you are a beginner, right? So I've done this daily. I still do read a lot. And that's how I keep myself and my research team up to date. We have journal clubs. We organize so many things. So anyways, yeah. So one thing probably I didn't include here quickly. So I don't have time for the case study, so I'm going to skip over that. So I have 2 samples, but I'm going to wrap up with this. So yep, sorry guys. So let me find the right slide. Here we go. And then in 2 minutes, because we're out of time. All right. So if you want to learn more, I have all my YouTube videos, the courses I taught at Imperial and other institutions online. So you have graph theory, machine learning, introduction. So I try to explain in really step-by-step way, and the intuition behind deep learning, why they came up with that idea. So if you understand the intuition, you're able to design easily, because usually we just learn by memorizing, and memorizing doesn't enable you to design creatively, okay? So you need to understand the intuition. Graph learning also, if you want to, try a few codes, everything is available. We have more than 65 published papers with codes available. And then, yeah, so different oral presentations. You can watch the videos animated, papers animated. These are presented at different workshops or conferences, and you can learn from the videos if you want. Okay, so all this is on the Basira YouTube channel. And just to recap, so there's one thing I wanted to do. Actually, I included that slide. I don't know why it disappeared. So guys, make sure that you read rebuttals. So you go, for example, to MICCAI website. There's the available reviews. You go to ICLR conferences, NeurIPS conferences. If you don't know these conferences, Google them up. You have ICLR, NeurIPS, ICML, AAAI, MICCAI, IPMI. And you can find on Open Review and on the MICCAI website the published papers with their reviews. So the best way for you to learn how to master is to think as a reviewer, and the reviewer is a person who's going to criticize your work. So if you go over like hundreds or even dozens, not hundreds, okay, dozens of rebuttals of your best favorite papers. You will learn how to argue. You'll learn how to, design logically. You will learn why this paper has been accepted as an oral or as a poster or rejected. And all of these are available on the internet. You just type ICLR open review, you Google it, you find the website, and you find all years from 2025 all the way back to, I don't know, 2000-ish or something. Okay, so you have a lot of data to learn from, but you cannot make GPT, learn, how do I say, like, you cannot just use GPT to do your things or LLMs. You need to train your brain. And of course, you can use AI for design thinking, but this is not what I'm teaching today. Maybe another day I can tell you how to use AI in a smart way, not to destroy your brain, but to enhance your intelligence, and that's something different. But yeah, so anyways, try to rely on yourself, build your personal intelligence, natural intelligence, enhance it through all these rules that I shared with you today. And there are so many things actually that I'm covering here. So for example, you need to know how to formalize a problem first. You can state your problem beautifully. Like this, like in these boxes, you find these examples in published papers. As I said, you define your hypothesis. What am I hypothesizing? Like this is an oral presentation paper at Grail, I think last year. And yeah, so you have a lot of things you can do. I think this document, okay, so I'm not probably going to share it unless you email me because this is a course I'm teaching. I'm still working on the book. But yeah, so the idea is for you to do this at the end. So that's my advice. So to read a paper, then try to, fill in the blanks, define the problem, write it yourself, okay? Articulate it yourself, identify the challenges, the hypothesis, and rewrite the solution using your own words without copy pasting. That is an important exercise for design thinking. And this is the last thing I want to share with you. And if you guys go to Slido, please, I would like to have a quick survey. And I'm going to share the results. So let's go to the slido.com again. And here we go. This is the RISE. It will take 2 minutes, and I'm happy to take your questions. The survey is on. You can join, and you can also type in your questions. Actually, I can add an Q&A audience. So I have a Q&A in the live on Slido, but I also have it here. So I'm happy to take your questions. Thank you. That's the end of my presentation.
Thank you so much, Islam. And then really, like, I believe everybody learned so much during this session, and then we have so many questions. So like, actually, like, I think we can extend the session a little bit more. The next session will start at 3:30. So
Oh, really?
maybe,
Fantastic.
yes.
So then I can do the case study if you guys want. Not sure.
Yes,
So
and maybe we can also leave a little bit time for the Q&A session. There are so many questions there, and I believe that
fantastic. So let's do a lot of
yes.
Q&A. I love Q&As.
Yes,
They're
and then
part.
maybe that's left maybe 5 to 10 minutes for the next session so that the next speaker
Yes,
can get prepared.
I totally agree. That's
Yes.
pretty cool. And I can see many of you are already on Slido. So I can also get your feedback. I'm going to share it also. Cool. Yeah. So let's start with the questions then.
Yes. Can you also see the Q&A session, or should I read it for you?
Let me check where it is. Okay.
Because there's a lot, and then I think it might be
Q&A. I found it here. Okay.
easier.
So I can, definitely. I'll go over it right now.
Yes.
Okay. So
Yes,
let me do it
perfect.
myself.
Yes.
The rest of image form segmentation or only focus on the object of interest. So in the example of the tree. So Rehab, it depends. So I'm not sure I'm getting your question here, but you can do both. I guess, of course, you can exclude the rest of the image. So when you're trying to segment, you just want to focus on the object. So in the input data, you can mask the input data will have the background, right? So somehow you can remove the background and try to find the objects, because the background could be, for example, the sky, could be, it depends on where you are. So if you want to spot trees and birds and like flowers and mountains. So these are different objects, right? So it depends on what you want to spot. But usually deep learning models are quite good at taking it all in and then getting you what you want. But if you want to do it hierarchically, so then you need to define the multiple steps, and they need to be logical independent. I'm not sure I'm getting your question, but sorry about that. Feel free to email me if you have further questions not clear. All right. So 1 second. So let me do this. Okay, cool. The second one, 2 models in the case. The first is one that does the denoising, yes, and the second one is that does the segmentation. That is correct. Yeah. The hierarchical breaking. So the hierarchical breaking is so easy. So let me give you another example. So for example, do you guys know what sample selection is? Sample selection, it means you have a training data. I have 1,000 samples. Let's say 500 dogs and 500 cats, and I want to classify, okay? So the 500 images of dogs may have a lot of redundancy. I may not have a lot of, how would I say, a lot of diverse data. Also cats. So hierarchical selection means I take that set of 500 and I select the most diverse samples, okay? So I learned how to do that using clustering or different similarity learning. There are so many tools. And I bring that 500 down to 250. Now this is hierarchy. And then from the 250, I split 200, 200, and I subselect maybe 100. And then from within the 100, I subselect a 50, right? So what did I do here? So basically from the 500 dogs, I ended up with 50 dogs, and from the 500 cats, 50 cats. So I brought down my sample size, my training data size from 1,000 down to 100. So this would be easier to train, faster to train. And this is, you know, a sort of a clustering within a clustering within a clustering. Like I'm trying hierarchically to build a pyramid while I take in all data and slowly I'm decreasing the number of samples until I get the best number of samples or the best samples that will maximize my accuracy through gradient optimization, right? So it's a whole field called, you can call it hierarchical sample selection. So this is one simple idea. You can apply it to samples. You can do it to features. You can do it to, you know, different types of neural networks. So it depends on where you want to apply this really a very generic principle. Yeah. So Vincent, would, for example, the hierarchy of initial low-level and deep high-level features in UNet encoder decoder segment can be example of breaking a model into hierarchical. Yeah, absolutely. I'm happy actually you got that. I was going to talk about it, but because I don't have time. So by the way, the deep neural network has sequential, you know, breaking, but also hierarchical blending. It beautifully combines both, because when you start, you know, when you use CNNs, you have large, you know, like convolutions, and then you make them smaller and smaller and smaller. And so there's a hierarchy there. So even in the UNet, right? So basically you're trying to minimize the size of the patches. So you go from large to smaller, smaller, smaller. There's a pyramid. So yeah, of course, that's a very good point. So there is hierarchical also breaking in the deep learning models, particularly UNets. And combining both may enable this. So you can keep, if you keep the same size, you may not be able to do the same thing. So that's why you do down sampling and up sampling, yeah? So well spotted. So is the ensemble always of same family of algorithms, or could it be a combination of totally different ones as well? It could be of different ones as well, but it depends how you're gonna combine them, right? So for example, it's actually a very smart question. So yeah, so if I think about the brain computes, the brain has a cognitive, you know, capacity. It has, it memorizes, it computes, it memorizes. It also, I would say, you know, solves problems. So there's problem solving. So if you say, I want to build a machine that is able to memorize, to compute, and also to solve problem, right? So I'll have a module, memorization module, a memory module, or a memory network, just calculate a calculus or compute network, and then I'll have a problem-solving network. And if I aggregate them in a very creative way, so the aggregation here is hard because now the algorithms, they perform different tasks. Then you can, of course, assimilate how maybe, I mean, not even a mini brain, something similar to the brain works. So the answer to your question, for the independent breaking, yes, you can do different things actually that can stimulate new ideas, but you need to have a rationale why these algorithms or these tasks should be aggregated at the end. So they should be codependent, somehow correlated. They should help each other, support each other in solving a bigger task. So this task cannot be solved alone. It needs to be solved if all of them are in parallel at the same time. So the logic behind this is similar to what I've just explained. And there are so many things actually in biology and nature, so many things operate in this way. If you guys read a little bit about biology, that would inspire you a lot also. So your drawings are, oh, thank you. It's amazing. Thanks. Thank you. Blending approach, just whoa. Okay, cool. Yeah, I love blending. Could blend of only different types of data sources used to create new solutions. Instead, always grouping algorithms. Yeah, absolutely. So blending different data sources, that's a very good thing. So there's cross blending. There's blending at the data, so that you have the data level, you have the model level, have optimization level, you have what else? So yeah, so data optimization / model. So you can blend at different levels. Okay, so if you say I am the first to ever use text and multimodal images to do diagnosis, all the literature, they either use text or use images, but I'm the first to design this model that operates on these two. Then that is blending, yeah? And it's innovative because you're first to combine these two data sets. So now it is innovative from a data blending perspective. Is it innovative from a model perspective that will enable your paper to get accepted to MICCAI? So that depends on how cool is your model and how smart is your model. If you're simply banding or changing a few parameters in an existing model just to integrate the text as a channel through node to VAC, that's not innovative, okay? Still, conceptually, that is innovative. So you really need to show that you are not solving this one problem incrementally, but if I get to solve this problem, I'm solving a bunch of similar problems. And that's how you design cool solutions, yeah? Or AI solutions in general. The paper. So Tasneem, I'll share the paper in the resources on the website. So I think Esther will do it. Okay, so can Professor have advice on undergrad students who can like break has research right there? Yeah, undergrad students. Actually, interestingly, guys, Lilian, yeah, Lilian. So 50% of the publications from my lab are from undergrad students, and we got so many main MICCAI papers in the past years. I think the key thing is like to use your undergrad project and make sure you engage, you start reading papers on your own. You try to approach professors or supervisor who are keen to do research and advise you, and like they want to kind of take you to the next level and like work on exciting research projects. But it is definitely possible to get a few publications before you graduate, okay? But my advice to you is to try to learn by yourself. It's hard, but try to learn by first lectures, like just, completing machine learning, completing deep learning, if you don't have those. But if you completed them already, then you start reading MICCAI papers, ICLR papers, as I mentioned, these top conferences, and really go through the rebuttals, go through their videos, try to read and understand. If you have friends like you who are interested in learning, form a group of friends and say, let's form a community. Let's get together and discuss this paper. If you have a professor who is available and who has a journal club or who wants to kind of, you're very keen, you say, I really want to do this. I just want to be there, who welcomes you, then just approach them. So you need to be in your life proactive, okay? Things will not come your way unless you're very lucky to be in an environment that things are there. But if things are not there for you, you just, make it happen, yeah? So can we attempt, these first? Yeah, of course. But so how would you, Sayanta, okay. How would you submit your work to these conferences? You need to get the spirit of these conferences. Like for me, over the past few years, I never thought about these conferences, right? So recently I started thinking, I was like, okay, so let me start a journal club. Let me understand the spirit of these conferences, right? Let me understand how they write, how they think, how the papers are drafted, how the methodologies are designed. So you really need to grasp the spirit of a conference to maximize the chance of your paper getting accepted, right? And Yeah, so you can't just switch quickly, because that would give you lots of rejections and it could be intimidating, but it's okay to get rejected, by the way. That's the way it is in academia. Gets rejected, you revise, actually take advice, revise, and submit, resubmit. But yeah, so for you to be able to submit to AAAI, ICML, ICLR, or all these conferences, like even MICCAI, like if it's first time, you really need to grasp the spirit. Grasping the spirit is applying the 6 rules: reading papers, analyzing their papers, thinking about design thinking techniques, how they write their annexes, how they design their experiments. You do it alone. If you have somebody with you, that's even better, because you can cross-communicate, a friend, a colleague, a professor. And yeah, so you get it from there, basically. But you really need to understand the spirit. And if you understand the spirit, you can use these design thinking techniques to design new methodologies. Thank you, Rihab. Yeah, I have so many. Jafar also. Trube, cool. Yeah, so so the Slido is still on, I think. I'm going to show you the results in a bit. Sequential learning. Okay, so questions. What are the thoughts on using MLDL in a pre-processing pipeline for another network? Of course. Okay, so you can use deep learning and machine learning as pre-processing, of course, but you need to really explain why. You can't say, I'm just pre-processing using a deep neural network, my image, and then feeding it into this neural network that does segment. If there is something that already fixes that and solves it, why you need to use another deep learning? Yeah, unless you have foundation models that you want to fine tune or something like that. So whatever you're doing, whether pre-processing or processing or post-processing or explaining what you got, you really need to explain why you are solving it in that way. And the key thing in design thinking is, like, when you guys are designing and taking notes and designing your model, think about, do I actually need this component? Why do I need it? Can I put it before or after? Can I add more components here? Why do I need them there? Why do I need to actually do the denoising F and then S? Maybe I have an explainability module that will explain the segmentation model. Like, so I have an explainer network, right? So now I'm adding things, and these concepts, right? They work together. So you really need to first get the logic, and that's the hardest part. If you get the logic, which means I'm thinking, I'm reading, I'm understanding how things work deeply, then you can do design thinking fluently, okay? So another question, most of the time during researching, we went away from main thinking. How to overcome this? We get away from the main thing. Okay, you get away from the main thing. Okay, so you get distracted. So basically, I understand. So this happens to me. It happens to everybody. You start reading about a topic, and then you find a word, you don't understand it. You open another paper, you find another word. Like, for example, I start reading about image segmentation. I find the word manifold learning. Manifold learning leads me to, subspace learning. Subspace learning leads me to Riemannian geometry. Riemannian geometry leads me to optimal transport. Optimal transport leads me to something else. And all these are new to me. And it happens to me before. So my advice to you guys, take it easy and keep tracing your reading. So what I do, I map everything in a log. So I have a notebook, whether on the computer or a hard notebook, and I write down what I'm doing. So today I'm going to start with, maybe, I don't know, like transformer models. So that will lead me to something else, maybe diffusion models that I don't know about. So you really need to learn the principles and understand step by step. And GPT these days can make wonders in teaching you things. You can go to ChatGPT and write, can you give me a simple example of how transformer works using, real data, simulated data, and explain step by step the math, the derivations, the attention, how it works. What if I change the number of heads? So you can learn so many things from GPT with real detailed mathematical examples, database examples, toy examples. It depends how you prompt it. So if you prompt it well, it will teach you everything. You have also AI coding. You can use AI software to code with you, right? So you can do so many things, but the hardest thing, as I said, is the design thinking for now. So GPT is not as good for design thinking. You can use it to prompt or give you ideas, but it is hard for it to kind of do blending. It's very hard. I've tried it, right? Because it's hard. It struggles for now. So hopefully I don't know, I say hopefully or not hopefully. If it cracks this, it creates everything, then what's left for us? That's a different question. Okay. So anyway, so for now, what I'm saying is like you can leverage ChatGPT to understand key ideas from paper to paper to paper with some toy examples and go over the math and understand how this works on data. And once you understand that, then you take a code and you try to code it up, right? So you really need to code. Otherwise, you will forget about it if you don't use it. Use it or lose it, we say, right? So yeah, and then you can write down. It's important to write down all these things. And then you say, okay, where did I start? I ended up with transport, what is it? Optimal transport, but I started all the way with segmentation and I went through all of these things. So where am I right now? Okay, what do I want to focus on? So you need to have some multi-pathway exploration. You explore different methodologies, but at some point you really need to focus on one thing. So it is okay to be lost and to have so many things to work on, because at some point after this exploration phase, it's like a wave, go like expand, and then you're gonna, contract. Okay, so you will focus on something, and you need to explore and understand different things to be able to focus and pick something you're excited about, and you think, oh, this is actually really cool. I really want to work on this, and I know that there are limitations here. So let me get started with this gap. Yeah.
I'm very sorry to interrupt, Islam, but due to the time, maybe we just leave one more question
One
and then
more
we wrap
question.
it
There are
up.
so many questions. Okay, so let me pick one.
Yeah, or one or two, like, yeah, and then we leave some
Right.
time for the
Okay.
next presenter to prepare.
So, anonymous about Xingyu Zhao talk about generalizability and sample size. So it's a big problem. I'm not saying it is solvable, but definitely collecting more data will help. Second, you can train fair models and you can use debiasing algorithms. You have a session later with Fahmy on fair AI in medical imaging. So there are some methodologies that you can use to teach the model how to not discriminate against, different sensitive social factors. And yeah, we can teach the models even on a small data set to do so. But ideally, of course, you want to collect more data. But it depends. Sometimes more data doesn't mean better performance, by the way. It depends on the quality of the data, the diversity of the data, and many other things. Yeah. So that was the last question. Sorry, guys, I couldn't get all the questions. There's Ahmed. I think he rose his hand. Yeah. So I don't know if I get that, but if not, that's fine. So I'm gonna
Maybe
share.
not.
Maybe
Yeah,
not.
but
Okay.
yeah, but
Yeah.
maybe let me ask something that I saw people asking, and I think is more important. Like some people ask, where can they get the case study if they wanted to try it themselves?
Oh, the case study. So the case study that will be, it's just a story I wanted to share, a true story. But yeah, so you'll find it on the website. You guys have the rise-micai.org, right? So the summer school page, you have all the material of the speakers. So I think the material of all speakers of the summer school is available to you here. Rise, let me show them, micai.org, right? And then if you go summer school, so mine would be available later. So I'll share the material to be uploaded here. Like here, you can download slides, videos, etc. Okay, cool.
Perfect.
Very nice. Thank you so much. Thank you, guys. Thank you I'm happy that you have slightly improved confidence and you like this session. Fantastic. Thanks.
Thank
And
you. Thank
good
you
luck with the
all.
rest. Good luck
And
with the
then
rest of
thank you so
the.
much, Islam. Yeah, thank you
Thank
for
you.
this so wonderful talk. And I believe everybody learns a lot. And there's like questions coming up. And then I'm so sorry, I have to make it stop because in 4 minutes we'll have the next speaker. And then now we will take the pause of the recording, and then we'll get some time for the next speaker to get ready.
Fantastic.
Okay. Thank you so much, Islam. Thank you so
Bye-bye.
much
Take
for this
care,
wonderful
everybody.
talk. And
Thank
then
you.
we will see each other, for the participants, we'll see each other in 4 minutes again. Yeah.
Okay, cool.
Yeah, hi Nina. Can you please set me as the co-host? And do you mind if we record the session?
No, of course, absolutely. Please do.
Thank you so much.
And thank you very much for the very kind introduction. So as you were saying, I wear a couple of hats, and you're going to see some of those today. Not only with the work that we've been doing on using real world data, which is one of the reasons we started working on generative models and subsequently diffusion models, but also via the work we started 7 or 8 years ago with NVIDIA with Project Monai. So I was one of the 2 funding members of that consortium, which now has become this huge international consortium of many, many institutions all over the world. And we're going to be using Monai in the second part of today's session to implement and do the hands-on of how diffusion models actually work. So moving on. So the plan today is that I speak a little bit about diffusion models, what they are, how they work, and hopefully giving you a little bit of the understanding and intuition as to why they became so practical, why they became so popular, and what makes them different from how generative modeling of imaging data primarily was done before. I will then go into some slightly more advanced topics, talking about different sampling strategies and conditioning, and you're going to see what that means. And then I'll take you through some applications later on. Then in the second part of the session, this will be after we do the 30-minute intermission, I will do a hands-on session where we are going to be going through code. So initially the intent was that we would go through a piece of code and you would implement things yourself, but now the summer school has become so popular and so large that it's a bit hard to do it interactively. So what I will do is I will give you access to some code, which obviously you can open from your side. But I created a little small presentation to take you through the code, and I'll show you line by line what the code is doing and how would you then use it for your own purposes. And that touches upon both DDPM type models, but also latent diffusion models, which are much more useful for example, 3D applications, even though we are not going to focus on 3D during the hands-on session purely because of a question of time. Right, before we then go into this, diffusion models, what are they? Why do we need them? How do they work? I guess that's the main set of questions. So the first thing that we need to think about when we think about generative models is that what we want is to have a model that that learns an underlying probability distribution of P of data, right? So here we have P of data, and we want to have a model that can map some this underlying distribution into P of data, right? So the underlying distribution could be something that is known, could be, for example, you initialize it with some random Gaussian noise, and out on the other side comes an image. So the goal really is to model that P of theta, the parameterized distribution, so that we can approximate P of data. And there's many ways to do this, and many of them which are taught in kind of relatively basic or introductory courses to machine learning, primarily if you have any computer vision. For example, autoencoders and GANs would be the 2 most popular ones. So these are classes of models where you are mapping some underlying dense distribution in the form of a vector and output. So the model decodes whatever you want as the output, in this case, the image. There's also other family of methods like normalizing flows and diffusion models, which obviously are ways of solving this. And there's many things that you can do with these kinds of models. Originally, these generative models were estimated specifically so that we could calculate the density of the data itself, the likelihood of the data. So if you observe a sample X, some image, one thing that you might want to ask is how likely is this image to be observed? So you want to calculate P of X given these parameters and this model family that you use to estimate. You also want to sample from it. So sampling from it is what people would call generating synthetic data. So when you look into the world of latent diffusion or all of the kind of generative models, for example, even the ones that exist in OpenAI, what you're basically doing is you're sampling from new data. You give it some prompt, some conditioning, or you might not even give it a prompt whatsoever. You might just say, give me a new example. So you give it a new X and you want to calculate what the output of that model is, the decoded output of it. And the last thing that you might want to do with generative models is to create unsupervised representation learning mechanisms. So this is ways for us to take some observed instance X And by using the model, we want to understand what the underlying latent representation will look like. This could be, for example, a vectorial representation, a dense vectorial representation of the image. It could be a tokenized form of the image. For example, if you go into ChatGPT and you give it an image, there's a visual transformer that basically maps the input data into a latent representation. And that model can be made generative. And that latent representation is important because if it has the right form, if it distinguishes the right parameters, if it has the right structure, it can then be used for you to be able to control what the samples look like and the shape of the distribution itself, which is super useful for many, many downstream applications, as we will see later today. So when you start looking into different types of generative models, these are kind of the ones that most people would start thinking about, right? They will start thinking about autoencoders. That's the most vanilla one. So an autoencoder is a model that would take some observations X. So this is the second one here in this list. It will take some observation X. It will pass it through an encoder, which needs to be trained for which the parameters we do not yet know. It creates a latent representation Z. Then it decodes the data back into the same format as it did when you had the input. So it estimates this X prime. And then you compare X prime with X, and you want X to be the same as X prime. So basically what you're saying is if I give it an input, you want the model to give me the input back or to try to reconstruct the input. But it needs to do this by mapping the data to these latent representations Z, right? These vectors Z. And Z is normally much, much smaller in terms of number of parameters, number of variables than the original input, which means what we're doing is we're taking an input image, compressing it to a much smaller vector, and then decompressing it or decoding it back to the original domain. And you want to train the parameters of the model so that this compression and decompression, the encoding and decoding that happens is optimal from the point of view of preserving what matters with regards to what X looks like. So this is what an autoencoder is. And a variational autoencoder is a formulation of a standard autoencoder where you basically put variational Bayes theory on top, which basically ends up being a regularizer on the space of Z and also a slightly different sampling scheme that you would use there. But there's many other ways to do it. For example, if you have GANs, in a GAN type setting, you have the generator part, so you're mapping a latent variable Z into the space of X, but you want this X to be indistinguishable from a real image. So if I generate an image here, this X prime, and I give X prime and X to a discriminator, my discriminator ideally should not be able to distinguish X from X prime. So it should not be able to say which one is the real input and which one is the generated data. So if I optimize the generator to generate really good quality samples, my discriminator should become close to random in terms of its performance. You then also have other types of models, such as flow models. Flow models tend to be less used on images or these kinds of data. They tend to be more used on distributions or vectors. And that's because of their computational complexity and sometimes the kind of the characteristics of the models themselves. But I think what's interesting about flow models is that the transformations in flow models are invertible. So in these two previous examples, D and G are in this case the encoder decoder of the VAE. They're not the inverse of each other, even though they're supposed to be doing inverse operations, right? They're mapping X to Z and then Z back into X. So in theory, they should be invertible, but they're not. And with flow models, we can actually build the network infrastructure with some specific constraints so that F of X and F minus 1 of Z give you basically the input back. And that is really useful when you're trying to, for example, model probability distributions themselves and want to have likelihood terms that are realistic as an output. But because of some of the constraints that these flow models tend to have, it's often harder to get good quality samples out of it. And last but not least, we have diffusion models, which is what we are going to be looking at today, which just use a very different way of thinking about the data. So while GANs and VAEs and flow-based models map an input X to a latent Z that is much smaller than X prime. And the reason that you want it to be smaller is because, and normally you want Z to have a certain form. For example, you want Z to be Gaussian distributed, so that if you want to generate a new image, for example, with a VAE, you generate a bunch of Gaussian random samples for Z, you decode those, and you have a new image. That's what you would do, for example, if you want to generate a new image with a VAE. So you need to be able to learn how to sample from Z. That means how you get new random variables from Z. And normally for you to do this, we want these things to be a multivariate dense vector. So a vector which is a multivariate Gaussian, for example. The problem with doing this is that this compression and decompression means that the amount of information that is stored in Z is less than the amount of information that was there in the original images, which is why VEs and GANs and flow-based models often tend to have limited performance when it comes to image fidelity and some other constraints, which I'll talk about in the future. While in diffusion models, the main difference is that the latent representation Z, which in this case is known, a Gaussian random sample, is not dense, but is spatial. We'll see what that means in a second. So there is this sampling trilemma, right? On one side, you have quality, you have speed, and you have coverage. GANs, so generative adversarial networks, are really good at generating high quality and very fast samples, but they lack what is called coverage. What that means is, a GAN, for example, will have a property called mold collapse. Not all GANs do, but most of them would do, where the model, for example, if you say, learn how to generate dogs, the model will not learn how to generate all types of dogs. It will only learn to generate a certain species or a certain type of dog, and it will kind of ignore another types of dogs. And the reason for it is because these generative adversarial networks only need to be able to trick the downstream adversarial network that the sample that they generate is real. So if it never generates Chihuahuas and it always generates Huskies, for example, it's very hard for the downstream network to know that the sample is fake because, let's be honest, a Husky is still a dog, and that's perfectly fine. When you have variational autoencoders and normalizing flows, they tend to be really good, and they model the distribution really well from a point of view of speed and coverage. But the samples you get out tend to be really poor. So you end up with blurry images that have really nice capture of the probability distribution itself, but the fidelity of the image, from our point of view, from a human point of view, the images then tend to be of very good quality. And then you have obviously the noising diffusion models, which is the ones that we're going to talk about today, which have really high quality and are able to cover all of these tails of distribution, so they don't do mode collapse, but they can be slow. And the slowness is something that has been worked on for the past 10 years, actually not 10 years, 7 or 8 years since these models were invented, where we see newer methods solving for some of the initial limitations that diffusion models would have in terms of sampling speed. So when I talk about unprecedented quality, it really means this, right? So if you look at what you can do nowadays with ChatGPT, or if you prefer, and you go to Midjourney or Google Gemini, any of those, where you can write basically a text prompt, and on the other side comes out an image. Those images tend to have a very high quality and realism. Obviously, sometimes they still look AI generated. That's getting better, and the models are getting better and better at getting certain patterns right that make it look less like an AI generated image. But you start seeing that they have some really broad realism, consistency, and control. So nowadays, you can prompt models to be very, very specific, to the point that you can even prompt models to write specific text on image. You could say, I want to have an image of a shop that says this thing as the name of the shop. And the model will learn that that word that you prompted with needs to go into the model to be able to generate that image and to be able to create something that is realistic and that will pass the check. Obviously, this means that if you can do this with natural images where you have billions of samples, you need to also have models that can achieve the same in a medical setting. And that is really much easier said than done. And why is that the case? The reason for it is that in standard natural images have a huge variation. However, we often don't see inconsistencies unless you look very, very locally at things. For example, there was a time where most of these models will not be able to generate hands very well. That's getting better. But nowadays, there is even things that you can very clearly see as being issues of these models. For example, the symmetry between the eyes of human beings, or specific skin patterns that you would expect to see that you don't see, or certain morphological issues that you will see in terms of the shapes of bodies and animals and etc. So And this happens even when you have access to billions of samples and associated text that has been written around those samples. On top of that, natural images tend to be 2D, while in medical scenario, most of our data tends to be 3D. Yes, we can take slices, and many people do that. But if you try to solve for the 3D use case, actually the 4D use case where you might have 3D volumes that are multi-modality, for example. You might have 5D use cases where you have 3D volumes that are multi-model and multi-time point, where you basically want to generate a video, let's say a heart beating, right? When you now have these kinds of setups, the networks that you would use and the volume of data that you would need to be able to use these technologies in an unblind way, where you just throw the model at the data and you hope that it works, these models start breaking down. And that's what makes medical imaging so hard, is that there is a balance to be struck between the amount of data that we have and the richness of the label of the text that we have that describes those images, and the complexity and the dimensionality of the problem that we're trying to solve. So 3D, for example, is really much harder than 2D, even though they look like similar problems. So if you look into the medical imaging side, the popularity of these models is really growing quite a bit. There's many kind of applications, all the way from anomaly detection and denoising to using these kinds of models to generate synthetic data, to be able to segment images. It just became a really popular way of thinking about generative models and to be able to encode the idea of a generative model in a way where you still have the high accuracy of semantic models, so models that work in pixel space rather than mapping images into dense representations. So how do these diffusion models work? And I'm going to give you first the intuition, and then hopefully I'll go into a little bit of the mathematics. But the intuition is actually the most important part. And this sounds like one of those situations where the method sounds so simple, but at the same time, when you then think about the mathematics, they all work out really well. So how does it work? If I give you an image, and if you open an image into Photoshop or something like that, it's very easy for you as a user of Photoshop to take an image and to add noise to it, right? So if you take an image and say, I'm going to add a little bit of speckling noise on top of it. Adding noise to an image is very easy. We just say, I want to sample some random numbers, and I'm going to superimpose these random numbers on top of my image. I can do that again and again and again, which means if I start with an image, I add a little bit of noise, I have this image. Then I have a second image, I add a bit more noise, and I have this image. And I added a little bit more noise, and I get the other image. And at this point, you're probably thinking, okay, why is George telling me about adding noise to images? That's completely not the point, but it is. What I'm trying to say here is, we know very well what the forward process is. We know how to start with data that makes sense with images, and we know how to make that, how to degrade that data by adding noise until what I have on the other end, by adding enough noise, I get to the point where the thing that I see is just noise, right? So if I'm on this last column here, the only thing that I can see there is pure noise. So if I pick up my little marker so that I can highlight stuff, right? Here, my observation is pure noise, which means I don't have very good models to generate these images so far, right? I do not know how to generate these images, but I know how to create these things. How do I create these things? I mean, if it's pure noise, I can just generate noise. Pure noise is indistinguishable from this noise that I see here. And you can still think about, okay, but why is that useful? Why is it useful for me to generate noise? The reason for it is because if you can learn to add noise by small steps, right? You're learning what is called the forward process. And you know how to do this explicitly because we know how to add noise to images. The next step is to do the opposite, is to say, okay, so if I start with noise, can I learn to make it slightly less noisy, and then slightly less noisy, and then slightly less noisy, right? That means I am transforming the problem of adding noise, which is the forward process, and saying, can I use a neural network to learn the process of removing noise? That means that if I start from a state of pure noise, and I go through multiple steps of removing noise from this image, the neural network that has been trained on this inverse transformation, right? Because here I know what my original image looked like and what the image with a little bit more noise looked like. And it knows what my second image with a little bit more noise looked like compared to the one before. So my model can learn all of these different mappings, and it can learn how to remove noise from an image. And if you now remove noise multiple times from an image, and you keep doing it over and over and over again by thousands of steps, what you basically are doing is you're transforming a pure noise image into an image that has structure, in this case, into an image that you will consider to be a real image. And it sounds a bit weird to say that we're transforming noise into an image, but that's literally what it's doing. The model has learned to create structure from randomness. So when it sees a Gaussian sample of noise, it learns to transform that Gaussian sample of noise into a slightly less noisy Gaussian sample that has a little bit of structure, because he has learned what horses or what cars look like. And the next time I take more noise, I'm now not starting from the original noisy image. I'm starting from the slightly less noisy one, and then from the slightly less noisy one, and the slightly less noisy one. So the way you should think about it is every time I remove noise, every time I denoise my image, I'm adding a little bit more structure and removing a little bit of noise. And then I denoise it again, I add a bit more structure again, I remove a little bit more noise. And slowly, I am building an image. And if this model has learned a consistent image-wide representation that has learned how to denoise images, it can then generate images accurately, even though the process that is learning is just the process of denoising an image. Okay, so how does this actually work? If I now go into kind of a neural network type application, first of all, there is this thing called the time chain. So the number of times that you add noise to an image to make it go from the actual image to pure noise is the time steps t, big T, right? So this will be this number that you see here at the top. So at t equals 0, the image is perfect, while at t equals big T, the image is pure noise, right? That's what we want in terms of setup. So how do we simulate noise? What we do is we say, I'm going to sample from epsilon. So epsilon is just a random noise vector. So I'm going to sample from a random number generator from a distribution that has mean 0 and an identity as a covariance matrix. So we just want these things to be independent samples. And I want epsilon to be really small. So what I want to do is to take x0 and add epsilon, but I want to not add epsilon fully. I want to add a certain amount of epsilon. Let's say alpha is 0.01, a very small amount of noise. So I'm taking the original image and adding a very small amount of noise. That gives me the slightly noisier version of the first image. And then, or depending if alpha is big or alpha is small, you might end up with a noisier or less noisier version of the image here. And then what you want is to be able to predict what the original noise was that you added to the image, right? So you want the neural network to say, if you take x0 and you add alpha t multiplied by epsilon, right? If that's what you're doing, what you want basically to ask your, so this is what this image here is here, right? If alpha is big, then this image is going to look like pure noise. If alpha is small, this image is going to look like x0. But what you want is to be able to say, if I give you this input, can you give me back that number, right? Can you give me back the noise that I've added to the image? So can the model predict what was the noise that I've added to the image, given that I give it a noisy version of the image? So it's trying to predict back the noise that I've added to x0. And if I know what the noise is, I can go into this image here and I can remove the noise again so that I could get x0 back, right? So you could say, how can you remove the noise in one go? Obviously, it's really hard to do that. But if you do it in multiple small steps, you can actually make this model converge. So this tells you how do you add noise to the image. And it tells you that the neural network's task is to predict the noise that I've added to the image so that I can remove it from that image later on. So if I now want to generate a new sample from the data. What I want is to start from a sample of pure noise. So I say, I want to start from pure noise. I'm going to give pure noise to my neural network, and my neural network is going to predict what is the noise that I should remove from pure noise so that I can get an image that looks closer to what I want my images to look like. So when I go through one step of denoising, the thing that comes out here would be a slightly less noisy version of this initial input. And then I give it to my network again, it predicts noise again, I remove the noise again. I give it to my network, predicts noise again, and I remove the noise again. And if I keep removing noise and removing noise and removing noise and removing noise, after I go through, let's say, 1,000 steps, I will have removed all of the noise that I need to remove, and now I have something that looks like a brain coming out on the other side. So you should really think about as the network learning what the inverse process is of adding random noise to an image. You're learning the backwards process of adding random noise, which is something that we know how to do. So to further understand the intuition of all of this, there is this little diagram here that people normally use. But before we even go there, we're going to kind of take a small detour into score functions, right? A score function is the gradient of the log probability of p of x given the parameter theta. So it's basically calculating the log probability of that part there, right? So that's the log probability, and then that's the gradient of it. So, right, this gradient here is the score function. And what's interesting is when you are sampling from this, the gradients that you get out of this, they point towards the regions of high probability, right? Because if you imagine that you have a probability density function, think about it as a Gaussian here and another Gaussian there with the different isolines. If you calculate the gradient of the log probability at, for example, this point here, you'd expect the gradient to point in that direction because that's the direction where the probability would increase, right? That means if I randomly sample from this space and I end up with a sample which is in this location, what I want to know is where should I move my sample to, how to denoise my sample, where should I move it to, so that my sample moves into the location where I have higher probability. So the score function is basically telling us how do we move random samples that were initially placed randomly in this two-dimensional plots into the location where the high probability or high density points are of these distributions, right? So it tells us how to update x to increase the likelihood, which is p of x, under the model. And by learning this score function, we are really, like, the learning of this score function is the thing that is at the very center of diffusion models. And if you think about it as particles, if you think about getting a particle into any of these two-dimensional plots you see here, what the question you're asking with diffusion models is where should you be moving this particle so that it gets to the point of high probability? And you could say, oh, but what does this particle mean when it comes to an image? Imagine you have an image that only has 2 pixels, right? Pixel 1 and pixel 2. Obviously, our images are much more than 2 pixels. This would be our pixel 1, and this will be our pixel 2 in X and Y. So if I start by randomly sample from pixel 1 and 2, I might get the value 0.5. Sorry, I'm trying to draw with my trackpad, 0.5, right? So if this is my sample that I randomly sample, the location of that sample is going to be here at the center of my plot, right? And now what I'm asking my model is, how do I transform this initial random sample, which is some number, so that it looks like the probability that I would expect, so that it looks like an image that I would expect? And what my model is saying is that these images here will look real, these images there will look real, but images that look like this will not look real, and images that look like this will not look real. So if when I randomly sample from the image, I happen to sample from here or here or here or here, the model is going to move these samples in the directions of high probability so that the numbers I end up with are going to be distributed around this probability density area and this probability density area, right? So I'm changing the pixels so that they move to an area that is higher probability by learning this score function, by learning this gradient. So the problem with score matching is that score matching directly is intractable, and that's because of this gradient of the log probability. That's just intractable to be able to calculate. However, score matching via denoising gives you an approximation, a mathematical approximation, and I'm not going to go through this because this is not the right venue to go through that derivation, but it gives you a mathematical approximation that allows you to predict what this gradient of log p looks like. And if under certain assumptions, for example, under the assumption that the amount of noise that we add to each point has a certain property, in this case, for example, that we're adding Gaussian noise every time we are creating more and more noise on the image, then there's actually some criteria and some ability to show that the model can converge and learn the backwards distribution as long as the step is small enough, right? And again, this comes from integrating ODEs and all of that theory that comes from ODE, from the ODE world. So there's this really amazing paper from Pascal Vincent, which is really good. I would really recommend you that you read it, and it gives you kind of a very good link between what the score matching function is and denoising autoencoders, and he kind of tries to create a little bit of a mathematical formalism between the log probability view and the fact that these denoising autoencoders are trying to do the same thing as are trying to approximate what the score matching is doing. And it's kind of one of the better papers I've seen in terms of linking the mathematics with the practicals. The other part that I think is particularly interesting is the fact that depending on the amount of noise that you have, the gradients that you estimate are going to be different. What I mean by this is, for example, if the point is here, right? Let's say I start from this point and I want to know how should I update these points. If I look at this density here or this density here on the other side, right? If I look at these two densities, the density on the top right has much higher density, much higher probability, right? So in theory, this point should be moving in this direction, right? But because I've not added enough noise and I'm looking at log probabilities, the gradients that I see at this point are actually of roughly the same scale going this way and going this way, right? Which means if I put a point here in that location, I will be equally likely to go to the top right corner or to the bottom left. That's because the gradients are roughly of the same scale and they're not informed by things that are very far away because the gradients are still local. You're learning a local gradient structure. However, when you add more noise, right? In this case, this amount 3 of noise, right? The one that is on the very right. By adding more noise, you're smoothing out these fields, and by smoothing out, what you see is that, for example, if the sample is in the same location, let's say here, now the vector is actually pointing in this direction. It's a small vector, but is now pointing in that direction rather than pointing in this direction. Because by blurring more the space, which is the consequence of adding more noise to the data, you are forcing the network to more likely go in the direction of the part of the field or of the domain that is higher density. So if I first calculate gradients at this scale, so that my point starts moving from here to maybe there, and then I'm now at this point, and I calculate the gradients using this noise. So I'm going to move from here to here. And now I'm here, and I'm going to move from here to here at a different noise level, right? The level at which I calculate the gradient should be a function of the amount of noise that I have. So earlier in the sampling, I want to have a lot of noise so that my gradients are pointing in the directions of high density parts of the domain. But as you are getting closer to these maxima, you want the amount of noise to be smaller so that your gradient can direct things to the precise location of that maxima. So there's a balance to be struck between how far away do your gradients travel and how informed you are about the full domain, or how precise do you want the editing of those values to be when you're getting close to a maxima. And that's why in denoising models, the amount of noise that you add at each step goes up, so that when you are denoising it back, you're going from a sigma 3 type model at the very beginning where the image is really noisy. And when you're closer to convergence, when the image already looks right, you are just changing the numbers very precisely so that they look like a real image, but you're not changing the structure globally anymore. Right? This is another kind of illustration of the same thing. If I take points, think about, again, these points that are in this domain. So these are a series of points that are located according to this spiral thing. And I'm going to add noise in terms of the location of the points. So the points are going to kind of start wiggling around. And if these points wiggle around and I add a little bit of noise, I end up with this. And if I keep adding noise, I'll end up with that, right? So you can see that by adding noise to the XY coordinates of a pixel, you're kind of spreading them out until they look like this. And you see that at one point, this thing just looks like a Gaussian point cloud. That means I can now learn the opposite, which is to denoise them back into this form. So you're kind of saying, how would I move these points so that they start moving to the direction of higher density, and how I can move them further so that they are aligned with this kind of spiral that I would expect. So this is the thing that I'm learning, right? The model that I'm learning is this thing, is how do I reverse the process that I've added at the top of adding noise. And if you think about what do the gradients look like, they look like the ones you see below, right? So a point that is here is going to move up, and a point that is there is going to move in this direction, right? And after these points start moving in that direction, my gradient changes. And now I'm going to follow this gradient. And now after my points are in this state, they're going to move to another location. And now my gradient changes again. So at every step, I need to recalculate what the gradient is, what my next location of the points are. And by giving many steps, these points will slowly move into the shape that you'd expect, because that's the shape that the network has learned as to the locations that those points should be, right? And again, this is a two-dimensional plot showing where these points are in 2 dimensions, but always make the analogy between the two-dimensional plot and an image with only 2 pixels, right? An image with 1,000,000 pixels is nothing more than what you see here, but rather than being a two-dimensional plot is a 1,000,000-dimensional plot, which obviously is not possible to visualize, but that's what you should think about an image, right? It still has the same forms, it still has high density areas, it still has structure, but the structure, rather than being a spiral in a 2D representation, is some manifold on some higher dimensional representation. There's also other ways to look at this, right? So if you think about this from a frequency point of view, if I add a little bit of noise to an image, and if this noise is Gaussian, so think about it as kind of a constant amount of noise in frequency domain that you're adding, right? By adding a little bit of noise, most of my signal still remains, right? But the more noise that I add, the harder it is for me to preserve my signal compared to the amount of noise that I have. So when for bigger t, I'm going to add more noise, and my signal is going to be indistinguishable on the frequency side. But for small t, my low frequency parts are all going to be there. And my model now is going to be focusing on these high frequency bits, which are the parts that have still not been learned. So as the diffusion process is happening, as we are going from big T, high noise, to small t, low noise, the models first learn the low frequency components of the data. And as they start converging to smaller and smaller t's into less and less noisy images, you start getting more and more signal out and higher frequencies, up to the point where the signal is so small that the model can really focus on those very high frequency signals. So if we now start thinking about, okay, what about these Gaussian perturbations, right? We are talking about adding Gaussian noise to data, which might not be what we want. And the reason that I say that is, even though Gaussian gives us some really nice properties in terms of the optimization and the step size and the Euler integration that happens on that ODE integration, the types of noise that we want to add to the image don't necessarily need to be Gaussian, right? We can think about other types of noise, soft diffusion, cold diffusion, different noise models, purling noise that is structured. But basically what we need to do is to add noise up until the point where we create an image that we know how to sample from. Random noise is very easy, but if it is some other form of unstructured noise is also okay. but we want something that the model can then learn the structure and invert. And Gaussian is just one way of doing it. And there's a huge amount of research happening at the moment on different types of noise that we can add to the data to then remove it later on. There's also quite a few different diffusion model formulations, which is why I didn't go into the specific mathematics, because if you're going to go for the DPMs or the DIMs or some other model, you are going to end up with kind of different solutions in terms of how do you schedule noise, how do you scale the gradients, how do you, for example, how do you create the distributions of noise? Are they Gaussian? Are they logarithmic? Like, there's all of these decisions that you need to make. And depending on which decisions you make, you might end up with slightly different models, but they all kind of work in the same way, which is why in the first kind of half an hour, 40 minutes, I was really focusing on the inner workings of these models rather than going very deep on the mathematics. The other part that I think is particularly interesting is that we were saying, oh, I want to learn how to denoise this image, right? How do we do that? The way we do it is actually really vanilla. We train a UNet, and most of you probably know about the UNet. It's just a semantic model that takes a tensor, which looks like an image, a 2D image or a 3D image as an input, and produces an output which is of the same size. And you want this UNet, which has initially been used for segmentation, to basically say, I'm going to give you the noisy image, and I want you to predict the noise that I need to remove from the input to get a slightly less noisy image. So the task of this UNet is not to segment, as in its original implementation. The task of this UNet is to predict the noise component of an input. And in the same way that you can use UNet, which is probably still the most used network, even for this purpose, you can also use any network that is semantic, where the input size and the output size is of the same type. You could use transformers, you can use VQVEs, you can use MambaNet, you can use any of the fancy architectures that you may wish to be able to make these things work. So let's move on to advanced topics and talking about conditioning mechanisms. So as we were seeing, the basic idea of diffusion models then is to have the forward process that adds noise gradually according to a certain schedule, and then having the denoising model, right, that learns to model these inverse transitions. And at each one of the steps, the model predicts what the next best location from the point is, plus a certain variance, plus a certain error. And that has to do with the type of noise we have, right? If we're adding Gaussian noise, we want the model to predict a Gaussian set of parameters, so a mean and a variance. And then we sample from that and we get kind of, this is the next location that we're in. So this Markov property simplifies the training and the inference, because you can say every single step is separate from each other. I can take step pair 1, 2, or 2, 3, or 3, 4, or 100, 200, and they're completely independent from each other. The only thing the model needs to know is the noisy image, what is the step that we're in, like they need to know the value of t of that step, and the only thing that the network needs to do is to predict the noise that I need to remove, right? So it's pretty simplistic in many ways. And when we're training these models, we randomly step in the direction that the model has predicted, and we add noise. So we're saying, oh, my pixels look like this. This is the next best location, plus a little bit of noise so that I might be a bit uncertain about what the next step is. And that's basically what we do. We do this multiple times until the model converges. So the model is predicting the noise that needs to be subtracted from the input so that it can recreate the input. And it's doing this by minimizing some loss function, normally something like the mean squared error. But there's many ways that you can achieve this, right? The simplest way is using what is called the DDPM schedule, which is the one that you've been kind of looking at. So the DDPM schedule is adding a certain small amount of noise at every single step, and it has many, many, many steps. So in this case, the steps are linearly spaced. They will be between 0 and t, where t is normally a very large volume, like 1000, right? And during training, we sample a time step t. We say, I'm going to sample as if I was in location t equal 150. I add that amount of noise, and I predict what the noise would have been compared to the location t 149, right? So the step before. And when I'm sampling, when I want to get a new image, I start with Gaussian noise, and I just iteratively go through all the values of t. So I start with t equals 1,000, then 999, then 998, 997, and I do this 1,000 times until I get my input, which is one of the reasons diffusion models are slow, because I need to give the input-output 1,000 times to do 1,000 steps, where every one of these steps I'm only removing a tiny little bit amount of noise. And the next step I'm removing another tiny bit amount of noise. And because I need to do 1,000 steps, I end up doing this process very slowly. So what does that look like? It looks like this, right? Where at step 1,000, it looks like pure noise. At step 900, to us, it still looks like pure noise. I would argue that maybe up to step 500, the image still looks like pure noise. But actually, if you were to, for example, take the image at step 500, and if you were to blur it, you will see that there's already some low frequency components that show like the shape of a torso with the patient's lungs. But you see that when you go from 500 to 400 to 300 to 200 to 100 to 0, that's where the noise, that's where the signal that we perceive as humans really starts showing up, right? And this Markov chain, this chain of many, many steps, means that the process is slow. So how can we make it faster? So rather than giving 1,000 steps, we want to do this in less steps. The first thing that we do, and again, all of these things tend to make the models slightly worse because you lose the stochasticity, you lose the small integrations. You just want them all to be faster, but these normally slightly worse in terms of fidelity, in terms of quality. So rather than stepping in one direction and adding random noise, which is what we do in DDPMs, in DDIMs, we are removing the random component, which means that we are just using, we're losing the stochastic or the random component of the model. And because of that, there's less wiggling around and you go more directly to the endpoint. If you do something like this, and if you have a noise model, which is a property of the time step t, you can also learn to do steps that are of bigger length, right? So rather than doing 1,000 small steps, you can say, oh, what if every time I step 2 steps in one time, right? Think about it as if you were doing gradient descent on some loss function, right? The gradient descent step size is probably one of the most important parts of an optimizer, right? Because it tells you, okay, I'm going to give this step, and now that I'm here, I'm going to calculate my gradient again to give another step. The smaller the step size, the more likely it is for you to end up in the local minima and to not go into some other random direction. But it will take you a long time. Well, if you give bigger steps, you might not find the minima at all because you might just jump into another mode. So in DVIM accelerated sampling, you are choosing the step size, and the bigger the step size, the faster it is, but the least fidelity, the least quality the model will have as an output. And there's a drawback to have between those two. And it's very easy to go from delta t to 2t, so going from 1 step to 2 steps, the quality is mostly preserved and you half the computation time. But when you start going to 5 or 10 steps at a time, the model can start underperforming really quickly. And a lot of research, again, is happening as to how do we accelerate by reducing the number of steps, but at the same time being able to preserve a lot of the quality that these images need. Now we're going to talk about conditioning mechanisms, right? So when we think about the problem that we're trying to solve, ideally, we would like to not just say, I'm going to give it random noise and I want to just get an image out. I want I want my model to learn the gradients of log of p of x, right? I want my model to learn that, but I want to be able to control in which direction I'm going, right? So if I go back to that 2-dimensional plot, I want to be able to say, I want to go to the bottom left corner or to the top right corner of this quadrant. And the way that I do it is by understanding what different directions mean from the point of view of the image that I'm going to generate. So if ultimately what I want is to say, I want to calculate the gradient of p of x, right? The gradient of the log of p of x given y, and y here could be, for example, a class. Let's say I want y to be dog, right? The class dog, or the class brain, or the class lung, or the class specific type of disease, right? If I want to say, what is the gradient of my image given that I want a lung, right? p of log the gradient of log of p of my image, given that I assume a certain class, just because of the Bayes rule, we know that this is going to be equal to the gradient of the log of p of x, which we already know. This is the thing we've been talking about for the last 50 minutes. But we can also learn the gradient of the condition itself, right? So this is the gradient of the log of p of y given x. And how do we calculate this? We calculate this by training a classifier to say, if I have this image with different noise levels, can you predict the class that this image contains? And if I can predict the class, I can then ask my model, backpropagate through this classifier and say, what is my pixel-wise gradient that will maximize my likelihood of my model saying that this is indeed a dog or this is indeed the lung. And I can feed those gradients into the DDPM equation and control the direction of denoising that we're seeing in these models. This is what is called classifier guidance. And in the classifier guidance, as I was saying, that's basically what we're doing, right? We're taking an image, the current state of my image, the current state of my noise image, getting my classifier output, and with this classifier output, I'm getting this gradient, and I'm using this gradient to nudge my diffusion model to go in a specific direction, which is going to maximize the likelihood of this classifier giving me the class that I want, right? So I'm using my classifier as a way to guide my diffusion process to go in a specific direction by calculating these gradients of the classifier. Just because of time, because I realized that I've been spending quite a bit of time at the beginning, I will probably have to jump over a couple of slides. But really, the thing that I wanted to say here is that the fewer noise steps that we give, the more of the original image we maintain. What I mean by this is if you take an image, for example, an image here of a cat, right? And I want to add a bit of noise, not completely add noise, but if I add a little bit of noise, so you still see a little bit of a structure of some ears here and a little bit of like a nose and eyes of some animal, even though you might not recognize that it's a cat anymore. You can take this cat, add a bit of noise to it, but then decode the cat under the class dog, which means you're keeping most of the structure, the low frequency signal that you would get from the cat, but you're now making it look like a dog, right? Don't forget that when you're adding noise, you first destroy the high frequency signal, and only later on you destroy the low frequency signal. So what's happening here is that I'm preserving the low frequency signal from the cat, but then I'm guiding my diffusion model to denoise the image back, but I'm guiding it by the word dog or by the classifier dog. And that means that my image is now going to look like a dog, even though he has preserved the shape or the low frequency part of the cat. Okay, so let's talk a little bit about medical imaging applications, because we saw some, but we didn't really see kind of what we can do with it. And this is going to feel a little bit like a medley, and I hope that I can still finish on time, even though this is going to be pretty quick now, because it took me a little bit more time at the beginning. First of all, image synthesis. In ChatGPT, you want to generate images because you want to see an image of a dog dressed up as Superman lifting a giraffe or something, and you just want to be creative. In our fields, we want to be able to generate synthetic data for many reasons. One of them is the fact that medical data has privacy concerns and governance concerns. So if we can learn the distribution of the data, we might be able to share the models rather than sharing the data itself. And we might be able to sample from these models rather than being able to sample and to just get the data itself. And people have shown that you can train these models on private data sets. You can run augmentation when training these models. You can search for edge cases, and you can train models that can generate very realistic images in 2D and even in 3D using a single unified framework. So in this case, these images here were generated using MONAI Generative, which is an extension of Project MONAI specifically for generative modeling, which is what we are going to be using in the second hour of this lecture on the hands-on session. And for example, you can show that you can start by random noise using these latent diffusion models, and you can generate high resolution or regional native resolution 3D synthetic brains from pure noise, guided by age, gender, specific physiological characteristics such as ventricular brain volume, or possibly even disease. That means you can learn what the space of data look like on the training data set, and you can then release the model and make that available to the community so that people can train downstream models. These models can work on the pixel space, so they can work directly on pixels, but they can also work on latent representations. So there is this subclass of models called latent diffusion models, which again, we are going to look at in the second hour, that learn first to encode pixels into a latent representation that is very dense, is a spatial latent, and then you use then a UNet to be able to denoise the latent space itself rather than the original pixels. And by doing this, you can make these models scale better than before. Obviously, there are certain concerns that come with these models, right? If you're training on the model and the models are really good at sampling from the data, there's been a lot of work happening on making sure that these models do not memorize too much, that they do not jeopardize the privacy of the original patients, of the original data. And there's ways that you can, for example, bring in differential privacy or privacy distillation as a way to make sure that the models learn global patterns of what the anatomy looks like without memorizing specific phenotypes of a patient, and thus preserving patient anonymity. And you can also use these models, for example, to sample specific rare cases. Let's say you have a data set with many, many patients, but you don't have many patients with specific diseases or specific conditions or specific sexes or specific ethnicities or specific age groups, right? You can use these kind of synthetic models to be able to generate more samples from the lower sample class so that you can get a model that is slightly more balanced in the end, and maybe a slightly fair or slightly more ethically calibrated model as the outcome. You can use diffusion models to do what is called image-to-image translation. So for example, if I give you a T2 image of someone's brain, I might want my model to generate what the T1 image or if I give you a T2, I might want my model to generate a FLAIR image of someone's brain. Or if I give you a CT MR image of someone's prostate, I might want the model to give me a CT image of the prostate. All of these things can be achieved with diffusion models. You can also train these diffusion models to be able to do what is called in-painting. For example, in this case, you have the cranium and you want to be able to reconstruct the missing bit of the cranium, for example, to be able to do implantation or implant generation, to generate the implant that this patient should have in their brain. So you start with the skull, which has a hole, you put a bunch of points and you say, where should this surface be? What is the shape of these points so that I can calculate a prosthetic, an implant, that is adapted to the shape of the skull. This is in surfaces, but you can do the same thing with images. In this case, you're asking the model to fill in the hole and to use the structure of the skull as a way to get you what the implant should look like. You can use it for the purpose of image segmentation. For example, if I have this image here, right, an image that contains 4 different sequences of MR, and I have an associated segmentation, rather than having an image which is 4 channels, I can add the segmentation as a 5th channel. And now, rather than decoding these 4 channels, I'm decoding 4 channels plus 1, right? So I'm decoding 5 channels in one go. And by decoding 5 channels in one go, I will then be able to basically reconstruct what the segmentation looks like from a segmentation channel which starts as being completely noisy. And last but not least, is anomaly detection. So the idea of anomaly detection is really interesting. And it comes from the idea that if you train the model to only, for example, only on healthy patients, if you give it an image of a patient that is unhealthy, for example, that has a big tumor, you can then ask the model to reconstruct that unhealthy image by adding a little bit of noise and decoding again, adding a bit of noise and decoding again. And by doing this, you're able to reconstruct an image that has reduced the amount of pathology that you see. And then by calculating the difference between the original and the reconstruction, you get some location where that abnormality has been. And there's many publications in this area where people have shown that you can partially remove these regions, that you can completely remove these regions by using certain types of methods. For example, this one here, which was published relatively recently, shows that you can remove really large stroke lesions and make them look white again, which means that when you subtract this image and that image, you get a very precise localization about where that part of the brain is. But ultimately, we are using these models to correct for certain things that are not visible on the training set, so that in the end, we get an image that is healthified. There's a healthy variant or a healthy version or healthier version of what the original image looked like. And by doing this, we can then detect where the location of the problem is. But we might just be able to detect if an image is healthy or unhealthy just by saying, if I reconstruct my image again, if my image that I reconstruct is very different from my original input, that means my image was unhealthy. While if my image looks the same as my original input or very similar to it, then my patient was originally healthy. So I will finish here. Hopefully this was a reasonable introduction to what diffusion models work and how they work and how to make them and how to train them. So we're now going to go for a half-an-hour break, but the plan is that in the next part of the lecture is going to be the hands-on session. We were planning initially to do it, as I was saying, with code that you would need to write yourself, but we're not going to do that anymore because of the lack of interactivity. But what I will do is that I will just open up the new slide deck. I will give you access to the new code, and then I will give you around 15 minutes for you to go through the code yourself and try to read the code and understand it yourself. So there's going to be an awkward period of 10, 15 minutes where you're just going to open the code by yourself. You're going to look at it, and you're trying to understand what parts of the code match with what we were just taught in this lecture. I will then take you through the code, one section at a time. And if we have time, I will then move into some slightly more advanced methods like different types of LDMs or different types of scheduling mechanisms, but we'll do that as we go along. You will have access to the full GitHub repo with a solution. So this is not about you doing something, it's about you just following the code and understanding what the code is doing. So I'll stop here. Thank you very much for joining me, and I'll see you in 27 minutes. So welcome back, everyone. So we're now going to move into implementing things, right? So I created this little slide deck in Beamer so that we can kind of go through the code and etc. But the key part is just as a very, very quick summary, right? There's two parts to what we will try to achieve today. At least part one, we will do it. Part two, we might not have the time depending on how things go. And the aim here is that we're going to be using MONAI, not because I'm trying to sell MONAI as a software package, but just because it will make our lives significantly easier in terms of being able to implement some of the tools that we would need, things like the different schedulers, the different mechanisms to feed the time point T or the noise model into a new net. Like all of those things are already implemented into packages like MONAI. But obviously, I will then ask you to, in your own time, to look into the code in more detail so that you can really see how things work. So today, we're really going to think about that at that high level, right? If we decompose the problem of diffusion models into the network, the scheduler, the training mechanism, the inferencing mechanism, we can build a DDPM model on one side. And if we now move forward and move into the LDM, so these are latent diffusion models, we first need to map images to latents, and then we learn the diffusion model in the latent space itself, which again allows us to use a standard variational autoencoder, allows us to build the latent diffusion models based on UNet and etc. All of it using MONAI, which is quite simple. So I will actually ask you if you could load up this link here, and I'm going to leave it here. So my proposal is now 4 o'clock my time. I would ask you to open it up and more specifically to look into, so this is going to be a link to VS Code, which is linking to my GitHub account. So this is a GitHub that I just created yesterday with the content for this tutorial. If you want, you can just go on GitHub and download the files to your computer if you prefer. And what I would ask you is for you to open the 2D DDPM tutorial, right, which is part one. As I say here, is the denoising diffusion probabilistic model DDPM tutorial. That's the one we're going to look at first. For you to be able to look at that, I will ask you to spend in the next 10, 12 minutes. Let's say we come back at 4:10 or 4:12. And hopefully by that time, you would have spent a little bit of time trying to read the code and trying to understand what's happening. And the reason that I want you to do that is so that you can see it with your own eyes before, and you get used to reading code and trying to decode what the code is trying to do compared to what you've learned in terms of the mathematics and in terms of the intuition that I just gave you. So please do spend the next 10 minutes looking at this, and in 10 minutes, I will then take you line by line in the code and show you what the code is doing. And then we can talk about some of the other tutorials, which we might still have the time to go through later today. So 10 minutes back to you, and I will call you back soon. I will share the link in the chat too, because that's what people have been asking me. Sorry, let me try to copy. I'm not sure I can send the link to everyone. You might need to copy the link yourself. I think I can only send it to the hosts and panelists, so apologies for that. But it should be relatively short. You should be able to just copy it. Okay, let's then go through, let's go through the code then. I hope you have the time to open the files to just explore them a little bit, and we're now going to see what they do. So just as a very quick recap, right? Diffusion models are these generative models that learn to create data by reversing these noising processes that we've been discussing about. And in the forward pass, what we do is we add noise to the data, and then we train a neural network to learn to do the opposite, to denoise the data. So the goal of this tutorial is to train a DDPM to generate synthetic 2D medical images. And we're going to use the MNIST hand X-ray images, which is around 8,000 images. And they have 64 by 64 pixel resolution. So we're going to use mono generative. And the problem is that it takes quite a while to train. So it takes roughly 50 minutes. So you're not going to see the training happening today, because it will take more time to train than we have to go through the results. But I will show you what the training will look like and what the outputs of the models will look like. And the key components that we need to put together is the UNet, so the network that is going to approximate that backwards denoising process. The DDPM scheduler, so this is the thing that creates the time steps, that predicts the next step, that knows how much to scale the noise by so that you can corrupt the input clean data so that it creates the noisy versions, and etc. And after we have all of that, we can use the diffusion inferrer to be able to train and to sample new images from the model. In terms of architectural components, we are going to be using a 2D UNet backbone. And the number of channels that the network will have is going to go from these 128, 256, 256. We're going to use attention. So attention is necessary because one of the things we need to give to the UNet is the time step t. In our situation, we're not going to be doing conditioning by external variables, which we could also do, for example, the classifier guidance type models. But what we're going to be doing is to just give it the value of t. So we say, currently t equals 0, or t equals 100, t equals 1,000, right? So, and in order to do that, we're giving this extra variable to the UNet. So it's not just the image coming in, the image coming out, is image coming in and a value of t going in. And in order to do that, we are going to use cross-attention to be able to have the UNet itself attend to the value of t so that it can change its weights and it knows how to predict noise better. We're going to use the DDPM scheduler for 1,000 steps, and that allows you to give just a beta scheduling itself. We're going to see what that means. We're going to use the diffusion inferrer that gives us the forward pass and handles the reverse sampling and does all of that for us. And we're going to use the Adam optimizer as is standard in these kinds of experiments. I mean, you could try other things, but Adam should be perfectly okay here. In terms of the data pipeline, there's multiple components there. There's a data transformation component where even though we start from a certain number of images, we don't want the model to just memorize those. So adding random affines or scaling intensities is the kind of easy thing. So adding augmentation to the model is the easy thing to do to make sure that the model sees slight variations on that data, even though we already have pretty large amounts of training data. So diffusion models respond really well to augmentation. So they benefit from it significantly, and they make diffusion models not overfit anywhere close to as likely, so which is really good. On the forward diffusion process, the process is, as I was describing before, we first sample a random time step. Let's say in this iteration, I'm going to get a random value between 0 and 1,000. I'm saying in this iteration, my t is going to be 152, random number, right? I then generate random noise, and I will use the equation that you see there, that equation xt, to be able to calculate the value, the noisy version of the image, which is basically a function of alpha. And the function of alpha is, again, a function of how much noise or how many time steps we're into the model. And then we're going to train a model to predict the noise xt, sorry, the noise from xt, given a certain time point t, right? So we give it a noisy image and the current time point we are in our Markov chain. That is going to give us a noise, and then we're going to take our previous noise estimate, remove the new noise, and that's going to give us the loss. So important here is that we're not predicting the denoised image. We're predicting the noise itself that we need to subtract to the image, right? MONAI generative is going to do a lot of that stuff for you, but we're going to see where that is in the model. So the model is learning the noise distribution at each step. And during inference, we are iteratively removing this predicted noise. So every time we pass the image through the model, we're removing a little bit of noise. Then we give this new image with slightly removed noise to the model again. We remove a little bit more noise, and we keep doing this until the image is noise-free, and thus will look like a normal image. MONAI generative has this thing that is called the inferer abstraction. And the inferer abstraction is able to do the forward diffusion process internally, right? So you give it the input image, you give it the model, you give it the noise pattern, and you give it the number of time steps, and it will automatically predict noise for you, given these inputs. So it does the internal scaling depending on the diffusion model that you want to use and on the noise itself that you sample from. And after you have the noise prediction, you can compare the noise prediction to the noise that you actually added to the image by calculating the mean squared error, right? So you have this noise prediction, which is the output of the model, which is a function of the input. And you have the true noise that you've added to the model, right? So this is the noise that you've added to the model, and the noise prediction is what the model predicts. And these two things need to be as close as possible to each other. But in this case, the noise prediction is predicted by the neural network rather than being something that we give to the model. And when we are doing the reverse diffusion, the sampling, again, we need to set up a schedule with a certain number of time steps, let's say 1,000 time steps. And then we say inferer.sample. So we're calling sample on the inferer object. We give it the noise model, we give it the model itself, we give it the scheduler, and the model itself is going to go through 1,000 steps. These 1,000 steps of denoising. So it's going to apply the denoising step 1,000 times until the image that comes out of the last application of the denoising step is basically our output, the sample that we have generated. There's a couple of small challenges which we need to be aware. One of them is that we need to, like the training step requires the random time step itself, the noise generation, the forward pass. You have to have some memory considerations, but basically this is relatively vanilla PyTorch code, primarily if you have the MONAI tooling behind you to help with some of these things. And what you will see is that after 75 epochs, we run validation every 5 epochs. We're going to see progressive quality improvements, and you're going to see what the mean squared error is going to look like on the noise prediction. And we will then look into sampling from the model and what the images will look like. So if I stop sharing now, and I now start sharing my Visual Studio code, and you are free to load up the code yourself, obviously. Let me just get the right window. Which is, yeah, found it. Right. So I hope that you can see the window. I hope that is big enough. I will actually make my window slightly smaller because it will zoom in on Zoom. So you should be able to see it slightly better than before. Okay, so the first thing to realize is that the code here is dependent on MONAI and Matplotlib being installed and all of the MONAI dependencies, obviously. So the first thing that it will do is that it will install that on your machine. I do not know how you will manage environments, your Python environments in your own local machine. So this is something that you'll need to do yourself. But after you install all of that, you can then import a bunch of tools that we will need here, right? We will need PyTorch, obviously. We'll need NumPy, we'll need Matplotlib, we'll need MONAI, and we will also need things like Torch, CUDA, AMP, if you're using a GPU device. We will use TQDM for us to be able to track progress. And we're going to load these inferers and the networks and schedulers from the MONAI generative package, which we have installed above, right? In terms of the data, we need to set up a MONAI data directory. In this case, we are creating a directory which we're going to put the data in. And we're going to set up the deterministic training purely for reproducibility. So setting determinism here is only setting a random seed, which in this case is set up to 42. Some of you might know why the number 42. But anyway, it's just a fixed number so that if we run the experiment again, we will get the same results up to some kernel randomness that might exist if you are using CUDA or NVIDIA tooling behind the scenes. So in terms of the data that we're going to use, we're going to download MNIST. So MONAI obviously provides tools for you to download MNIST. So you can just call MNIST dataset, give it the directory you want to go, you want to get the training part, you want to download equals true. You don't really care about progress bars or anything like that. And out comes the training data. And that allows you to create a training data list, right? So you now have the image and you have the class name. You want to find the items where the class name equals hand. So we are selecting from it. And that will create our train data list. So the subjects from the MNIST dataset where item class name equals hands. Train data list will then contain all of the hands that exist in MNIST, which is roughly 7999 to the images. We can then build these augmentation stack, right? And the augmentation stack is built out of a few things, right? There's a image loader that loads the hand images from the files. Then we call ensure channel first D. So it ensures that the original data is channel first, which is needed for most of these models to train efficiently. Then there is the scale intensity range. So it's something that just makes sure that we are min-maxing the data between 0 and 255. MNIST is already like this, but even within MNIST, there's a lot of variability in terms of the min-max of each one of the images. And now we're going to add a random affine augmentation. So we're wiggling the image around, rotating, scaling by a certain amount so that the images all look slightly different. Every time they go through a model, they will go through this transformation stack. And that allows us to then define our training data loader, right? We now have our training data loader. For validation, right, we want to be able to do the same thing, but we don't want to apply the augmentation. So now we're just loading the image, channel first, scale the images so they are all between 0 and 255, but we're not adding augmentation because we're just validating. We want to make sure that the model is doing the right thing. And because of that, we don't want to apply augmentation because we want to know what the truth is with a minimal amount of corruption. And if you want to visualize what the data looks like, it looks roughly like this, right? Where we do get the first element of the training data loader. We can then use torchcat to concatenate multiple images. In this case, the first 4 images of the batch that we're getting. And that we are creating this object called image visualization, which is, again, the concatenation of all of these images. And then we use matplotlib to do figure show and image show of the image itself between 0 and 1. And out comes this, right? So this gives you 4 examples of what 4 hand images look like. And this already starts giving you some insights towards the what the model is going to have to learn, right? First of all of these images have this weird label here, which comes from is a downsampled L letter for the letter L for left, which normally comes when you're acquiring X-rays of someone's hand. You want to label which hand is it, so that in the future you know if the hand has been one way or another, or which hand is it. So all of the images will have some label like that. You also see that even though in theory X-rays should be calibrated so that the background is black, is not necessarily the case. For example, the image on the right, the background is not fully black and there's this kind of illumination effect. There's also quite a lot of variation in terms of the size of the hands. It's very likely that the image on the right belongs to a child or a younger person, while the image on the left belongs to a bigger person, purely because of the size of the hand. It might also just be a different zoom. Don't forget that in X-ray, we don't have a notion necessarily, primarily in these kinds of images, of the scale of each pixel. If you're doing something like MRI or CT, where the pixel size is known, then you would have a notion of scale. Here, this is a camera, and the camera is going to take the X-ray picture depending on the zooming mechanism that you might have in the system. Okay, so the next step is to define the network, the scheduler, the optimizer, and the inferrer. I'm first going to define these things, and then I'm going to show you what each one of these things are doing inside to some level of detail. You will need to spend some time by yourself so that you actually understand this properly. So on the network side, we are using these diffusion model UNet. So a diffusion model UNet is very similar to a standard UNet. So a UNet that we use for the purpose of segmentation. with the main difference being that you prescribe the number of spatial dimensions. So you could say, I want to have a 2D diffusion unit or a 3D diffusion unit if you're doing 3D data, for example. You define the number of input and output channels. So in this case, because we're giving it gray level 2D images, we have spatial dimensions equals 2, number of input channels equals 1 because it's gray level, and number of output channels is also equals 1 because it's gray level. Then this number of channels is how many channels do we want in the different down and up sampling parts of the unit. So we're going from 128 to 256 to 56 at the depth, at the deepest part of the unit. And then these attention levels is when we are feeding the value of t to the model, so the time step t, we're going to say, this is the noise sample, or this is the noisy sample at t equals 152. Like we are sampling the value of t. This value of t needs to be used to predict the noise value. And this is done via cross-attention mechanism, which we'll see later on. And we need to decide at which levels of the unit. In this case, this is a 3-level unit. And we are saying here that we want attention to exist at the 2nd and the 3rd level, but not at the 1st level. It's just an experimental thing that you need to try. You can turn all of them on. You can turn some of them off. At least one of them needs to be on because otherwise the network doesn't know the time step t. And the optimality of this is a function of the amount of the training data you have and how do you want this influence of t to behave. And because this is attention, you also need to define the number of heads that you want on the attention channels, because in attention, you need to define that. Then on the scheduler is the thing that knows how many steps, how do you add noise, how much noise to add, how fast do you add noise. All of these notions of noise and noise prediction and noise definition and number of time steps and integration steps is all defined in the scheduler. In this case, Monai provides the DPM scheduler. So the only thing we need to say is we're going to do the DPM and we're going to use 1,000 steps, right? If you click over here, you see that you have the schedule, in this case, which the default is linear beta. You have the type of variance. You, for example, might want to clip the samples. You might want to have a minimum and a maximum on the samples that you're going to clip. There's a bunch of things you can define on the scheduler. And different schedulers are going to have different defaults, obviously, and different behaviors. But they will all have a series of methods that allow you to then link these things up in a downstream model. And then you define the optimizer, which is Adam, and you define the inferrer. So the inferrer is the thing that actually performs the forward pass, but that also allows you to sample from the model if you want to get new images, right? And for the inferrer, the only thing we need to give it is the scheduler. We say, I want it to be an inferrer, an object inferrer, which is built around the DDPM scheduler. So it will inherit certain things, certain methods from it, and it will define these methods. And out comes this inferrer. So the inferrer is the model that we will actually run the inferencing on. We will come back to these model definitions in a second. I think it's better for me to go first through the model training steps so that you see how the model training works at this high level, assuming that we have a network, we have a scheduling mechanism, and we have an inferring mechanism. And we will, after going through the model training, we will go through each one of the different models and schedulers that you see just up here. So either you can use a pre-trained model, which there's a Torch hub model that is pre-trained, but let's not do that. Let's focus on this one here with the else variable, right? So we're setting the number of epochs equals 75. We're saying we're validating every 5 iterations. And now we are going to enter our epochs, right? We're saying for epochs in range and epochs, we're saying for a current epoch in the range from 0 to 75, we want to do a series of steps, right? The first of them is to set the model to train, set the epoch loss to 0, reset the progress bar, and then we're actually going to enter this part of the function, which is the thing that is most important in all of this, right? So we are setting up the progress bar, we're zeroing the optimizer, right? So we're setting the optimizer to 0. We're fetching an image. We're saying, I want to fetch an image from a batch. I'm zeroing the optimizer. And then I'm actually going to do the denoising process. So what is that comprised of? First of all, I want to get a noise sample, right? This is something that is of the same size, rand-like image. So it's the same size of the image, but is random. So I say, here's an image. The image is 64 by 64. Give me a vector of random numbers, which is also 64 by 64, right? And I'm mapping it to device because I want it to be on CUDA or GPU if I'm going to run the next step. Then I'm going to say, what is the current time step, right? I want to say my current time step is, let's say I have 1,000 time steps, so I want a random number between 0 and 1,000. And so the time step will be a number, right? And again, today I chose the number 152, but so let's just keep that number for the sake of it, right? It's going to be a number, different every single time I pass through this part of the code. So now I have a sample of noise, which is the same size as the image, and I have a random number between 0 and 1,000. And now I'm going to give this noise and this time step, right? This time step here in the noise into my inferrer, plus my input, which is the image that I just got from my batch. So I give it the model, the image, the noise, and the time step. And the inferrer is going to give me back the noise prediction, right? So I gave it the noise, and it gives me back the prediction of the noise. So what I want is for this thing and this thing to be the same, or as close as possible to each other. So I'm going to set up a mean squared error, or an L2 loss, which is going to calculate the mean squared of the differences between the noise vector and the noise prediction vector, both in floats. And that's going to give me my loss function, right? So I'm giving my network, here's my image, here's my noise. Tell me what the slightly less noisy version of this image looks like, and my network needs to tell me this. And now I give this loss, and with this loss, I pass it through a scaling operation, and I call backwards on it. And then I step through the optimizer, and I call update on all of this. And I then track the loss by adding the loss of this item to the epoch loss. Right? By doing this multiple times over the different steps of a batch, you are basically accumulating this epoch loss, and you're calculating multiple forward passes for multiple images. And that allows you to go through, let's say, one epoch of the system. And then every time that, my epoch is divisible by val interval, in this case 5, so every time my number of epochs is divisible by 5, I'm going to be able to do a validation. And validation is something that is very similar, but now with one difference, right? Now I'm setting my torch to no grad because I'm not doing any training any further. Then I'm going to calculate my noise, I'm going to calculate my time steps, and I'm going to give it to my inferrer. And I'm going to calculate my validation loss, but now without applying any of the augmentation or anything like that. And I'm going to validate how good my prediction of noise looks like on a data set, which is external to the one that I've been using to train my model up there, right? So that's quite important that you appreciate that this is a different data set, is a holdout data set. So you do this basically multiple times, right? Every time you do this, you're updating the model to be able to make this prediction better. And then every 5 epochs, you validate the model so that you can track it. And the model training will look like this, right? Epoch 0, 1, 2, 3, 4. You see that the loss starts being quite high and it goes down really quickly. And at the beginning, even though the loss is small, the image that is being generated by the model when you decode doesn't look great. From epoch 5 to 9, the loss now goes from 0.017 to 0.0138. And you see that this difference here looks small compared to the drop that you see in the first few epochs. But actually, the image now looks much better. Not great, but better, right? Continued training goes from 0.0134 to 0.128, right? Even smaller drop than before. But now, suddenly, the image looks much, much better. With a bit of a weird thing. This person only has 4 fingers. So the model has kind of learned something, is starting to look sharper, but is still not globally consistent. It's locally starting to look better, but is not globally consistent. We keep training the model, and you see that the model, the performance of the loss is going from 1.34 to 0.034 to 0.0128 to 0.0117 to 0.0118 to 0.0116. and suddenly is getting into the 0.0109, and that's roughly where it plateaus, right? It plateaus at around the 0.01. It actually drops below that, but that's pretty much as good as it gets. Which means that as the model is training, it's kind of wobbling up and down, but you see that the quality of the labels that you're generating here at the end are really high quality. And that's because the model has learned better and better global structure. So even though your loss doesn't look much better, it's consistently lower than before. So if you look at your learning curves, which this is doing, right? This is using, if you're not using the pre-trained model, it's going to plot all of these things, and we're just going to visualize it. And you see that the train val curves look very similar to each other, so the model is not overfitting. And the reason that it's not overfitting is because we're running augmentation. If you turn augmentation off, you will see some overfitting. And you see that the model goes to a pretty reasonable loss function very quickly after around 5 epochs. And if you were to look at this and you say, oh, why don't I just stop training there? The difference in these generative models between this value here and the value here at the end that looks really small is actually super important, right? And again, this is a difference between epoch number 10, where this is the output we have, right? After epoch 9, 10, and epoch number 75, where the image is really high quality, right? If you look at his loss here, it looks like he has almost plateaued between those two, but he has not. With generative models, it's super important that you let them train for a long amount of time so that these models properly converge to a specific endpoint. If you now want to create a new image from scratch without doing the denoising process, you now go into what is called sampling, right? So what does sampling do? In sampling, you start from pure noise. You say, here's a pure noise image, which has been randomly sampled via a random number generator. And I give this noise sample to my inferrer in sample mode, and I say, go through 1,000 steps of denoising and give me the output image back, right? So I turn the model into a val mode. I get the random noise sample, which is a 64 by 64 image with random numbers. I set the scheduler to 1,000 steps. It's very important that the step setup is the same during training as it is during inference, at least for the DPMs. And then you give it infer sample, you give it the noise that you've created, right? This is pure noise. You give it the model that you've trained, you give it the scheduler, and you might say, like, save some intermediary images and etc. And the model is now going to run the inference process 1,000 times, and out is going to come this image, right? And if you then see this image, you can then use this torch cat to be able to see the intermediaries, and you can plot them. And what you see is basically this, right? Super noisy, super noisy, super noisy, super noisy. Seems like nothing is happening. But suddenly on the last 200 or 300 steps of the chain, you see a beautiful image of a hand coming out. You could argue that a lot of these first few steps are wasteful. And that's literally the reason why many people have started improving the sampling schemes. If most of the detail is obtained in these last few steps, can we skip these first few steps? Is there a way that we can speed this up? Because clearly it doesn't seem to be necessary for you to have a very high accuracy representation on the first like 700 or 800 steps of the diffusion process. Most of the detail seems to come in the last few steps. So is there a way that we can reformat this to make it work better? I hope it makes sense so far to everyone, right? So if I now go back up here, right, into the models, there's two main parts, or actually three. There's the diffusion UNet model, there's the DDPM scheduler, and there's the diffusion inferrer itself. If I first go into the diffusion UNet model, right, the diffusion UNet model looks like this. So he has loads of arguments that, that we were not really using there. But the key part here is that he has these number of levels of attention, and in which one of the levels do you want the attention to be there, the number of features per level, and etc., right? And he has a bunch of different methods that need to be defined for you to meet kind of these object criteria that the inferrer will then expect, right? Which is, you basically have a series of kind of definitions, depending if you have conditioning on or not, and etc. But then the main part is here, right? We're defining a convolutional operator. We are defining a bunch of selves which are given our inputs. We are defining the time component, which in this case is a time embedding. So we're transforming the time that we give to the model through a linear network to give us a time embedding. We are also creating a class embedding if we want to do classifier guidance. So there's a bunch of things like this here. And then we are creating the actual network architecture itself, right? There's two parts in a UNet. There's the down path, the encoder, and there's the upper path, the decoder, right? We first need to define the down path. And the way we do it is by setting a series of levels which are defined by the number of channels. So we are saying if we define 3 sets of number of channels, that means the network has 3 levels with X number of channels per level. And we are going to define these down blocks. So this is the architecture of each one of the levels is one of these down blocks, which is going to be a function of the number of input channels and output channels. And also, is it a final block? So is it the block that is at the very bottom of the UNet or at the very end of the network? And depending on these variables, which is given here as an input, or this variable, which is given there as an input, and is final block, we are going to create this object, which is the get down block. So that's a block within the level that also allows us to get the down block. There is the mid part. So this is the bottom of the UNet that does not go down or up in resolution. It just preserves the resolution. So this is specifically designed for the middle block of the network. And there's the up block. And in the up block is again similar to the down block where we're running it k times. And it's going to be again a function of the number of channels that we have in the previous output, in the inputs, and also on the previous level, because now we're concatenating from the encoder arm, but also from below. So this allows us to create these up blocks. And after we create these down blocks, middle blocks, and up blocks, we are going to use torch and then sequential to be able to glue these things together so that we can create the actual network, right? We then need to define a bunch of stuff. We need to define what the forward path looks like. This is very simple, right? We just create the time embeddings or the class embeddings if we're doing that. We are passing it through the down blocks. We might have additional residual connections if we're using control net, so we can ignore that for now. We pass it through the middle block. Then we pass it through the up blocks to go back through the decoder. And then you pass it through the output layer, which gives us H, and H is the thing that we actually get back, right? So this tells you how to build the encoder and the decoder. And the key part in all of this is every time we're building these down blocks or up blocks, all of these blocks are blocks with attention. So if you were to go down to the definition of each one of these blocks, you will see, and again, I'm not going to spend too much time here, that they use these cross attention blocks or attention down blocks or cross attention blocks, which basically enforce the time to be used as an attention mechanism so that the network knows if we are in step 1 or step 100 or step 1000, right? This is super important. So this defines our network itself. Then we have the DDPM scheduler, right? Again, if I go into the DDPM scheduler, the DDPM scheduler has a couple of things that we need to define, right? So the number of diffusion steps that we have, the type of schedule. So the type of schedule is how much noise do we add in each one of the steps and how quickly do we add noise. And depending on how quickly do we add noise, we then also know how quickly do we remove noise, right? And there's also some things about clipping variances to make sure that the thing is stable or not. So a scheduler is going to inherit from the scheduler object, and it's going to have a series of methods defined, right? One of them is the set number of time steps, where you're, again, as the name says, you're setting the number of time steps. You are getting the get mean. So this is every time you sample from the model, you get the mean and the variance, and then you step in the direction of the mean and add a little bit of noise, a little bit of variance to it. So you have to have a function that calculates the mean of the scheduler. You have the get variance, right? Not only you get the mean, but you get the variance. In DDIM, not DDPM, but DDIM that I was presenting before, the variance is 0. It doesn't exist, but you still need the method to be there. then you have a step, right? This is the thing that allows your model to do one step of your Markov chain. Again, it defines what that step looks like. And that's pretty much it, right? So if you know how to step through the chain, if you know how to do a forward pass through the model, and if you know how to get the mean and variance, you can give this scheduler to the inferrer, and the inferrer is going to take the model and the scheduler to know how to go through the multiple steps. So what does the inferrer look like? So the inferrer, again, it inherits from inferrer. It has a bunch of things defined. But the key things that you need to understand here is the sample part. So this is when I call infer.sample. This is what goes through 1,000 steps, for example, if it is the DPM of the scheduler, and is going to give me a full sample, right? So this is the for loop that will then compute the image. You see, calculates xt and xt minus 1, and is going to go through this x number of times, where x is, let's say, 1,000. There's other methods that you need, right? So you need to be able to do things like calculate the likelihood, so that with the likelihood, you can, for example, calculate some loss function, or you might want to use the likelihood for other purposes. You have some approximations which might exist for certain methods, but not for all. And ultimately, you define those. And if you define those will then give you a way to either step through the model, or to be able to do a full sample through the model and to get things from the other side. So on this front, on the diffusion model, you define a UNet with cross-attention that will be receiving also the time point t as an extra variable beyond just the image that we want to denoise. We have the deep DPM scheduler that tells us how to add noise and how to predict the mean and the variance of this noise schedule itself. And you have the inferrer that takes the scheduler and the model and actually creates the chain and does all of the inference itself and gives you the output. And again, as I explained before, you create the noise, you end the time step, and with the noise and the time step, you give it to your inferrer, which then allows you to calculate the noise prediction, which is where you get the loss from, which then allows you to optimize the system. So in a way, this is a very high-level view of how to build these models, which is comprised of relatively few steps. You create noise, you create a random time step, you give it to the inferrer, which has defined the model itself and the scheduling mechanism. And then you define your loss function, which in this case is just a residual between the predicted loss, the predicted noise, and the true noise. And that gives you a gradient, and that gradient is the thing you optimize. And with this gradient, you are able to train a better model to be better at removing the noise or at predicting the noise from the input image. And that's the thing that you'll then use to generate new samples. Right. I hope that made some sense. So we are, let me stop sharing and I will start sharing this again. So we will unfortunately not have time because I didn't realize this was going to take me this long, but we're not going to have time to go through all of the things, but you have the code, you can go through it yourself. But I will just take you a little bit through the next stage, which is to go to the latent diffusion model. So far, the process of noising and denoising has happened at the level of pixels, right? So your image was 64 cubed or 64 squared. And in 64 square, we are creating noise which is of the same size. And this is great if your image is relatively small. But for example, if your image is really big, let's say you have a 1080p or a 4K image from a camera, or if you have a full volume, like a 3D image of a brain, which is 256 cubed. If you do that, creating the denoising model at the pixel level is really hard because you have too many pixels, and the denoising process cannot really become very good at predicting how to denoise an image. So what you do is you build the noising model, you build the noise model on a lower resolution representation of the data. That means we are first projecting images into latents and then running the diffusion model on latents. So let's say the input image was 256 square image, right? Your image was 256 by 256. You're first going to train a model to go from 256 squared to a latent representation, which is maybe 32 by 32 by 3. And then you go back up decoder to go back to 256 squared. So you're compressing the original input from 256 squared to maybe 32 squared times 3 back to 256. So this is what this encoder and decoder are doing. So you're compressing pixels into a vector which still has x and y, right? So it's still a spatial vector, but now it has an extra dimension, which is depth, right? It will be like again, a 32 by 32 by 3 latent representation. And after you do this, you then add noise into these latent representations. So you take this latent representation, which you know how to decode. You can just pass it through the decoder if you want to get back the pixels, the image. So you now take this vector and you add noise to this vector, and you learn to denoise this vector, right? But now everything is happening on latents. And the reason you want to do this is because if you're working on something which is 32 squared times 3, that's much smaller in terms of number of elements that you need to learn from than the original 256 squared input image. This is even more crucial in 3D, where if your input image is 256 cubed, you will need a lot of data and a lot of compute to make that model work. While if you map that data into maybe, let's say, a 16 cubed latent representation, right? So you're compressing 256 to only 16 cube elements, plus like 3 or times 3 depth channels or n depth channels. You can then learn the latent diffusion model in that space, and being able to have a much more accurate model that can work with the amounts of data that are feasible to obtain in a medical setting. So you first need to train an autoencoder to compress the data into a latent, and then you run the diffusion model on the latent space. And after you run the diffusion model in the latent space, you can use the autoencoder decoder to get back the pixels. And this is much more efficient. So in this case, in the thing that you will see in the link that I've shared with you, is that you have the compression mechanism, which goes from 64 squared to 16 by 16 by 3. In this case, the latent representation is not much smaller than the image, but it is still already smaller. Obviously, this is much more important if your original input data was much higher resolution, which is not the case here. But it's still good for you to be able to train this. And the loss here is actually a little bit more complicated, because when you're first creating your autoencoder, that the only thing it's doing is compressing the data from 64 squared to 16 squared times 3, the loss there is a standard autoencoder KL loss. You have a reconstruction loss on the images, you have a perceptual loss, you have an adversarial, you have all of these things. After you train your autoencoder, you can encode all of your images into latents, and then you run your diffusion model on the latents as if they were images. They're not, they're latents, they're 16 by 16 by 3 vectors, but it doesn't matter. That's where you're learning your diffusion process. And if you now want to sample a new image, what you do is you go to the latent space, you create a pure random noise vector in latent space, you do the reverse diffusion process so that you can create a latent which is structured, so a 16 by 16 by 3 latent that is structured, and then you just decode that latent through your autoencoder decoder so that you can get the output image. So similarly to before, you have the autoencoder KL, right, which is the first level that maps images to latents. And here we are saying these are the number of channels, this is the number of spatial dimensions, these are the number of, and you see that by going down 3 times, we're going from 64 to 32 to 16, right? That's why we go to 16, because we have level 0, level 1, level 2. And the number of latent channels equals 3 is the fact that we want, as you saw here before, a 16 by 16 by 3, right? So it's 16 because I go down twice, by 16 by 3 because I have 3 latent channels, right? And because this is an autoencoder KL, which is only taking image and transforming it to a latent space, we don't need to give it any cross-attention mechanism or any time or anything like that, because I'm just mapping images to latents, nothing else. So the loss there is a simplistic autoencoder loss, which we have not really spoke about today, but if you have ever trained an autoencoder, variational autoencoder, or autoencoder KL, they all kind of look the same. They have a reconstruction loss, they have a regularization loss, and they might have some perceptive loss or adversarial loss to make it slightly faster. And then you need to actually train the diffusion model itself, right? But now it works on the latent space. So we went from an image to a latent. Now the latent is 16 squared times 3. And we now need to build a latent model. It's, again, a standard DDPM. But the DDPM, rather than being a 64 squared DDPM, is a DDPM that is working at 16 squared times 3. And because of that, we do not need that many levels of attention, etc. We can actually make the model slightly more efficient. There's a few things that you need to kind of figure out. For example, the latent space might not have unique variance. So normally, diffusion models like the data to be between 0 and 1 or centered at 0 and variance of 1. There's no reason why the latent space needs to have that. So you might need to do some rescaling. Again, something for you to explore. But after you do all of this, what you basically go through is through the LDM training process, right? So you take the images, you pass them through the autoencoder KL, which gives you the mu and sigma. And then after you are in that space, after you have this space of Z, that's the thing that you then give to your inferrer so that your inferrer will then go through the data and calculate your loss, etc. But everything here is now happening in latent space. And when you're sampling from the model, you start with a random vector, which is 16 by 16 by 3. You give it to your inferrer, right? So you give Z to your inferrer. Out gives you a sample from this. And you now need to give this thing to your VAE decoder so that it gets you the image back, right? So you're going from image to latent, latent to noisy and denoise latent, and then from latent back into an image via the decoder of the autoencoder, right? So you start by a 16 squared times 3 latent, you get, which is just pure noise. You get the structured latent, and then you pass it through the decoder so that you end up with a 64 squared generated image. So just to finish up, because I won't have time to go through the code, but I would really suggest that you go through the code and you'll see very clearly what these different steps look like in the code. It's pretty obvious when you're using something like MONAI because it really gives you those building block level things. The classic DDPMs are working at the pixel level at 64 square, while the LDM is learning on latents, which is 16 by 16 by 3. And it sounds like a small difference, but it's pretty huge, primarily when you're looking at data which is even larger as the input size, or in higher dimensions, such as 3D or 4D. The DDPM has a smaller UNet, while the LDM has a much larger UNet because that UNet needs to have more features to be able to learn things at that scale. And you also need the autoencoder to be able to compress it. And LDMs normally are a little bit slower to train. And the reason they're slower to train for this specific setup is because in the LDM world, you need to train the autoencoder first, and then the DDPM itself on the latent space. And those two things just take longer because there's two models to train rather than one. But when you sample, sampling from the LDM is much faster because you're sampling in latent space rather than sampling in pixel space. You have much lower memory usage because the diffusion process is happening at 16 squared rather than at 64 squared. You have better image quality because your latents have preserved the perceptual quality, and you can use things like perceptual loss on the autoencoder itself to project the data into the latent space. And they're much more scalable. So LDMs really give you a big advantage by going into latent space that allows you to scale to higher dimensions, to bigger input sizes, and etc. And in terms of results, right, it's pretty obvious. The autoencoder shows that you can create inputs and outputs, and the latent space is well regularized, and the quality of the reconstructions looks fine. And then the diffusion loss shows very similar curves to the ones that you saw in DDPM, but it converges even faster because the resolution of the tensor of the latent is smaller. So the space is smaller, and that gives you good samples. And if you sample from it, you see very sharp details, similarly to the ones you saw in the DDPM, but is a model that is much more scalable to larger resolution inputs. So just to finalize in terms of tips, right? There's a series of best practices that you need to think about when you're doing all of this in terms of hyperparameters. Starting with defaults is pretty good. You need to make sure that you're monitoring GPU usage. You need to make sure that you're kind of checking checkpoints regularly and etc. For the DVPM model specifically, the batch size is super important. It massively affects training stability. And you might want to look into DDIM for faster sampling. Again, things for you to explore. And I've shared with you Jupyter notebooks that take you through all of those if you want to spend time doing all of this at home. And for the LDM specific case, it's super important that you train the autoencoder to convergence first. Don't be lazy and stop the training of the autoencoder too early. Normally, that means that your latents are not going to have a good structure, and your downstream diffusion model is going to massively struggle to deal with an unstructured latent representation. That's the most important part for you to remember with regards to LDMs. There's many issues, which again, I'm not going to go through. You have access to the slides, right? There's memory issues, there's problems of generalizability. Most of these things can be solved by training longer, lowering the learning rate, having larger batch sizes, having bigger models. If you go for all of these things at the same time, you will probably end up with a model that works pretty well. We have not gone into conditioning and how do we bias these models to give you the type of images we want. That's not what we're going to do today. But if you are doing that, that's even more important, that you follow some of these common issues and solutions. There's loads of tutorials and resources. Actually, I would recommend that you go into the original DDPM and LDM paper. You can go into MONAI Generative, but you can also just look into the tutorials and notebooks that are there. They are super, super interesting, like small details that you might learn from those models. And they also give you examples about how these models would work in 3D or will work in higher dimensional latent diffusion models in 3D, for example, which can be really hard for you to train if you didn't have a resource such as MONAI Generative behind the scenes to help you get this working. Okay, so I'm 3 minutes over. Apologies for taking a little bit longer than expected. I hope you enjoyed the tutorial. I know we didn't really have time to go through a lot of interactive sessions, but I hope you managed to understand what the code is doing. Feel free to go to the link that was shared in the chat, but also just go to MONAI label itself, right? Sorry, MONAI Generative itself. MONAI Generative has loads of tutorials, and diffusion is one of the main components of MONAI Generative. So if you're interested about the topic, just go there, spend a little bit of time, and have fun.
Yeah, thank you so much, George. And I'm afraid we don't have much time for the Q&A because the next session, we don't have break between these two sessions. So yeah, next session speaker is ready and the co-host is ready. And I have already pasted the link to the code to the chat box, and everyone now can see it. So if you have any question, you can feel free to contact George. And thank you so much, George.
Super. It was an absolute pleasure, and I hope you enjoy the rest of the summer school. Bye-bye.
Bye-bye. Thank you so much.
Okay.
Excellent. Thank you. Sorry for this.
Thank you.
Yeah, thank you so much for the kind invitation. And so I was asked to bring a bit of material on the workshop we've been organizing since a few years now, called iMIMIC. So this is on the topic of interpretability of machine intelligence in medical image computing. You see the acronym iMIMIC. So I just wanted to give you a bit of intro background. The first one is like typical questions about why do we need interpretability? Here, by the way, I use the word interpretability and explainability to reflect the same, more or less the same principles. And you can see here reasons to why interpretability is desired. So you have issues of fairness, sustainability, transparency, accountability. You have this problem of a black box, and when the black box disagrees with the doctor, then the question is, how do we actually move forward with that? What if the system made a mistake and we go with that diagnosis and there are consequences because of that? So I like to first show you a video. This is a sort of a compilation of people that probably you have seen. These are colleagues from the AI general field, where they sat together to talk about why interpretability is important.
There are many settings where a deep model trained on enough data that exhibits enough accuracy on test data is all you really need to go, and you don't need to be able to see what's inside that black box. However, there are other settings where that's a very risky thing to do, even if you've got what looks like superhuman accuracy on the test data.
I resent right now that the neural net wave and deep learning wave has become so predominant that people say, well, that's the way to go. You just collect data and intelligence will work itself out. And that's just not true. I don't believe it. If you just take existing data sets and you put them into a machine learning system, the machine learning system will just copy the behavior of that data set. And if there's biases and it's been collected in unfair ways, then that will be just replicated in the machine learning system and probably augmented because the machine learning system will be used over and over again. The initial bias will get replicated. How do you fix that? How do you think about that? What are the legal issues that are involved there?
You know, you just won't know about these problems. You wouldn't have anticipated them in advance if you can't sort of open up your model and see what's happening.
I think if we want to tackle some very complex problem, that kind of interpretability is necessary.
There's some AI people that say, you know, look, it's a black box. It doesn't want to test that. Why do you need anything else? I just don't agree with that point of view. I think this is a multi-stakeholder thing with many people that need to understand and all participate in their roles. And I think explanations is critical.
Now, I'm okay using technologies I don't understand. I got here on an airplane and I don't fully understand how airplanes work. But I take comfort knowing that there is an entire field of aeronautics dedicated to creating that understanding. I would like to live in a society whose systems are built on top of verifiable, rigorous, thorough knowledge.
And we just find that every time we put on this magic glasses where we can see what's inside the model, we find an amazing number of things that are wonderful, but we also see things that are very surprising, very disturbing, and that no human would ever let get deployed until they found a way to fix it. And it's just so important to be able to put on the magic glasses in many domains and see these things before you deploy.
So this was a little promotional that for the year 2022 edition of the iMIMIC workshop. I'd like to next show you some of these concerns. So one of the issues that I, as a researcher, a developer, I'm very concerned about is something called shortcut learning. So what you see here, this is probably one of the famous papers on the topic of shortcut learning from Robert Giros, where they talk about this sort of principle of least effort, where the model will try to find an easier way to find the solution. Maybe the best way to understand that shortcut learning is with these images here you see. Let me just go straight for, I love this example with the cow. You can see a cow that's been detected, you know, by a model, but then this cow at the beach is no longer detected by the system, but because the system actually had learned to detect the grass behind. And the same happens with the distortions, where you could say, well, I still, as a human, I can still see the subject here in the picture, but the model cannot see it anymore. Or where the model is so prone on texture, but then the moment that texture is gone and you just have edges and outlines, a human can see, in this case a cat, but the machine cannot do it. So there's where we have issues in potential biases that are picked up by the model, and therefore sometimes the performance is actually higher, but in out of domains, in test time, in real life situations, that model might not generalize. You see here on the right, this was the time of COVID. This paper was showing a saliency map. So this is one type of approach, very popular, where you see pixels that are sort of important to the model. And you can see that many times the model doesn't even look at the lumps to perform. Another example was this paper in Lancet, where researchers here, they had trained models for the classical diagnosis, but then they also checked that these models were very good at detecting ethnicity. And they were actually very good at doing this across different imaging modalities and across anatomical regions. They use explainable AI techniques to then do things like that, where you see this heat map showing, well, these pixels seem to be important to the model to identify ethnicity. when performing some ablations, rerunning the model, they saw that effectively the model was able, at a very high performance, was able to detect ethnicity, and then when ablated, so those pixels are removed, the performance would drop dramatically. So if you train a model and you say, well, 94%, that's actually pretty good, and maybe I just stop there, the model is doing something good, and job done, right? But then there are issues that are under the hood that are very hard to catch. One example from our field, we were working also, as Yao Jung mentioned, we have an FDA system now deploying the clinics in the US for brain tumor analysis. So we were working this, you can see this was in 2018, and this was one of those moments where we realized interpretability is something we really need. We were working on a classification model. These are patients that have a brain tumor, and they are categorized between a low grade, you can live for years with a low grade tumor, versus a high grade that the prognosis is really poor. We ran some saliency maps, and we observed that the model was very interested in at the border of that image. There is no biology in those pixels defining low-grade gliomas or high-grade gliomas. When then performing an analysis of our pipeline, not the model, but the pipeline, we realized that the model was picking on those pixels because our pre-processing had a problem. Then when fixing that problem, we could then improve that situation, and even better, we could improve the classification accuracy of a model that initially was not bad. We could have said, well, almost a 90%, something we could use, but thanks to interpretability, we were able to then even improve performance of that model. So we started with the iMIMIC workshop. You can see here, this year is the 8th edition of the workshop. And the number of participants has been increasing. Back in 2017, 18, it was not known by many. And I remember that many times I would be asked, why to bother if the system is approved, the system is deployed and is working as intended? Why do we care about interpretability? But I think the evidence, it's been now enough to let us know that we have to work further on this topic. Here's some pictures of the last 2 years. You can see full rooms. It's been always as an organizer of such a workshop, a very nice experience. And I found this picture where one of our RISE organizers is also here in the discussion. Things we can do with interpretability and papers that are being promoted are many. You can see here different uses of what we call interpretability boosted AI, which is not only about explaining a model, but using these internals to things like quality control, actually using this information beyond pure interpretability, or using it, jumping here, on things like active learning, where we actually select samples that are informative using interpretability. To finalize, I wanted to then to show you what's going on now in the field. We need to go multimodal. We need to go also longitudinal. That's the clinical reality. That's the type of data. So the black box, in a way, is getting more and more complex because the clinical workflow is also of that complexity. So we've been discussing in the literature about how to move forward, how to integrate a so-called orchestrator that is able to integrate different modalities, different time points. Now, what happens with the area of foundation models, where we train this large model, or we use it from other lab, and we have this generic sort of Swiss knife approach that is then fine-tuned. There is research also showing that there are biases in these models. We don't know basically what's in that model, and we have to be careful about then what happens with those biases once we do fine-tuning, once we do things like distillation from one model to the other. Do we actually inherit biases and other issues? The road ahead for explainable AI, and this is what the workshop is also aiming for, is to bring the clinicians a bit closer. So radiologies and XAI, you can see here some statistics back from 2018 at the top, where radiologists in general do see the importance. So you can see here that they do want to have security about their answers, and their interpretability can help in that as a layer of quality. And this is very recent from my colleague Inti Slovik in digital pathology, also showing that overall 3 out of 4 specialists in digital pathology do see the importance of explainable AI. So the road ahead is that we need to go from a nice to have into a must to have. Now we, with language in our work, even more and more present, so visual language models and so, we need to start dealing with explanations. So we need to verbalize explanations. So there's also here, you see some examples of literature in a field called natural language explanations. So very interesting what's going on in the field, and the field also of like frameworks. What tools do I have available is also expanding. You can see here, I have different explanation types, different types of data for explanations. But the question remains, how do we go from a methodological field where we develop methods into a clinical workflow where the specific methods are properly implemented? So I will skip the video for the sake of the time. This was our promotional for this year. And with this, I finish, and thank you for your attention.
Yeah, thanks a lot, Mauritius. I mean, it's a really great overview of the iMIMIC. And then anyone who is still deadline is already over for this year or still open?
So as a matter of fact, tomorrow we are releasing the so if anyone here in the RISE submitted to iMIMIC, tomorrow the emails are gonna be sent out through CMT.
Okay, yeah. But anyone, maybe next year will happen again, right?
Absolutely, we hope to keep this going.
Yeah, great. Thanks a lot. And then the next presenter is Professor Uduna Anajoto. Are you there? Or Professor Uduna?
Can you hear me?
Yeah, I can hear you.
Okay, fantastic.
So yeah. So you wanted to introduce by yourself, or you want me to introduce yourself?
Oh, just go ahead. You can go ahead and introduce me.
Yeah. So Professor Uduna, we're gonna talk about the workshop MIRASOL. And Professor Uduna Anajuto is a neuroscientist at the McGill University, specialized in intelligent PET imaging to map brain health from molecules to mind, and a faculty member in the Department of the Neurology and Neurosurgery, and part of the neuroimaging and neuroinformatics group. So, and she integrates PET and MRI to detect early subtle change in brain functions and chemistry. And her lab focused on developing the next generation ultra high resolution PET system and AI-powered imaging tools to enhance the clinical brain imaging with unprecedented spatial precision and sensitivity. Welcome, Uduna.
Thank you very much. Let me see if I could share my screen. Just give me 1 second here. You can see my screen, right?
Yes, we can see your.
Perfect. Okay, let me just get my animation. I mean, my pointer. So where's my pointer? Oops, sorry, that's what I wanted. Okay. So, no, that's the wrong one. Laser pointer. Fantastic. Okay. So thank you so much for the invitation, and I'm just going to hide this so that it doesn't go over my stuff. So I'm here to speak about MIRASOL. This is the Medical Image Computing in Resource Constrained Settings Workshop and Knowledge Interchange, which is happening on September 27th at MICCAI. This is actually the second year we're running this workshop. It's just renamed, and I'm going to talk about that in a second. And I'm so happy to be speaking to you guys Obviously the paper submission has ended, but we are hoping to have this workshop happen again next year. And if you happen to be in MICCAI in South Korea, feel free to drop by and have a look at some of the papers, some of the innovations that are going to be presented at the workshop. So what's the main motivation behind having this workshop that's focused on enhancing imaging methods for resource-constrained settings? I'm just going to use brain tumor imaging as a way to illustrate why this actually matters. And this is because if anybody does brain imaging or even just does a little bit of cancer imaging, you know that there's multiple different imaging modalities that we tend to use to characterize the lesion. And in this particular case with brain tumor, they're very, very heterogeneous. They're also very complex and very difficult to treat. So sometimes we use, and not sometimes, in clinical practice, we use CT with and without contrast. We do multiple different types of MRI, and we even do positron emission tomography, so looking at molecular signatures. And sometimes we combine all three modalities. And that's a lot of information for a radiologist to look at. And you're also crossing this disciplines. You're going from nuclear medicine, which is where a lot of nuclear medicine physicians tend to read these images, to radiology. And if you look at in sense of where some of these resources are, because this is quite resource intensive to not only read these images, but also to start to characterize, even in some places classify which type of tumors that you have, or even be able to segment out the tumors to do further analysis, it kind of becomes very tedious and very time consuming. And in countries, most parts of the world, there's not a lot of trained physicians that are able to do this type of analysis within a short period of time. And also a lot of these physicians tend to see a lot more number of patients. The patients tend to be more complex because they tend to come in much more later in terms of delayed presentations, so they have more complex cases to look at. If you look at where the resources are in terms of hardware, scanners that we use to acquire these images, you see that places like Africa and most other low resource settings have less number of scanners available. And some of these scanners are not able to do some of this high level or multi-parametric type of imaging. So we have this huge disparity. And when we start to create methods that are sort of done in one domain, in one area, so in an area where we have a lot of these high level or multi-parametric imaging, sometimes it doesn't always translate. And I'm going to show you what that means. This is actually a very nice LinkedIn post. This post was, I think, I'm not sure why, maybe I didn't put the date in there, but this post was sometime in early March, where the chief medical officer of GE Healthcare, which is one of the leading medical imaging devices that we use, especially here in the West, kind of came up to this realization that most of us in Africa already knew for decades, that there are not that many scanners available in places in the entire continent of Africa compared to, say, one little city in New York like Manhattan. So we know that AI does have a massive role to play in the sense of being able to, and again, I'm going to use brain tumor to illustrate this, being able to provide not only diagnostic, but also prognostic information, and as well as in treatment, in this case for brain tumor, in tumor treatment planning. And I'm going to skip through this. There's obviously multiple class of types of AI methods, but over the past decade, at least at MICCAI, there's been a concentrated effort to really figure out how to essentially build models that can automatically segment these tumors, classify them, and make it much easier for computer-aided diagnostics to happen, especially for this very complex type of brain disorders. And so we've been able to amass quite a bit of data across the MICCAI community. These data sets are part of the Brain Tumor Segmentation Challenge data set that's been running for a long time. And these data sets have been ground, so we have ground truth validation. So these are expert-generated labels that allow us to not only be able to segment or create models that can segment and benchmark them, but also be able to sort of start to do classification between the tumor subtypes. However, and this is a very nice paper that sort of summarized the state of where we are in terms of, and again, I'm using brain tumor to illustrate this, the state of where we are in terms of using these data sets that have been aggregated from the community to create computer-aided diagnostic tools. So here, this is a summary, a systematic review that summarizes about 224 studies that have used either the BRATS data sets or similar type of data sets to create automated methods for tumor segmentation and in some cases classification. The take-home message is that they are starting to perform just as good as expert readers. However, we know, and this is from a work that one of my former students, Dong Zhang, who is now a PhD student at UBC, did, where we were actually trying to ask the question, okay, well, if we take some of these models that are top performing models that have been developed for lesion segmentation, so for stroke lesion segmentation, for example, the IELTS challenge, for BRATS, for brain tumor segmentation, for example, the BRATS dataset or the BRATS challenge methods, and then apply them to data sets that kind of are real world data sets, generic data sets, the way we scan or image in parts of places like Africa, how well do they behave? And so these are three cases. These are cases that represent different types of lesions, stroke lesion, brain tumor lesions. And these are some of the top performing models from a myriad of former challenges that have been done at MICCAI. And eventually you can see here that most of these models perform well when they expose them to data sets that they have not been generalized on. When we took essentially a simple, straightforward CNN method and essentially tried to train it to be aware of some of the imaging data challenges that are very common and obvious in some of these resource-constrained settings, you see that the performance does improve. What do I mean by the imaging environment or the way imaging is done in most places in Africa, and actually, to be honest, within most parts of the world, is that when you compare the type of data sets that we tend to see and use in most of the challenges that are done at MICCAI, or most of the data sets that are out there for methods to be developed, we find that those data sets tend to be rich in terms of high resolution. For example, for MRI, they tend to be at least 1 millimeter thickness, so they're much finer or thinner. You have multiple different contrasts, you have rich information, and you have thousands of cases. Now, when you come to most parts of the world, because 80% of the world does not have access to medical imaging devices like MRI or CT, you find that most of the times when they do have systems, they tend to be suboptimal, meaning that they have much thicker slices. So you're now interpolating a lot. You have fewer information, meaning that not all this types of contrast are available, and you have very few cases because of multiple different issues. One being the cost of care. So when we start to take this type of data sets and try to force or even transfer learn, or some of the methods that we're doing without having a very focal understanding of some of the challenges that actually exist within some of these regions, we find that our models don't always translate very well. And so I'm going to skip through this a little bit because some of these challenges, you may have seen or heard about them, but this is just a way to summarize some of the barriers, some of the challenges that tend to be common in resource-limited settings. And I've sort of grouped them into infrastructure-based, skill-based policy. For example, the predominance in terms of MRI, low-field MRI, lack of picture archiving systems. If you don't have the dataset archive, you don't have any data sets to actually train with, unskilled personnel in terms of both acquisition, analysis, and even interpretation of data sets. And obviously issues with just research ethics. People don't tend to de-emphasize this, or they don't tend to see the value or the importance of this. And I put this here because I'm going to use Africa, for example, because that's the region where I work. Part of my research happens there. Is that when it comes to medical imaging, most of the medical imaging devices are in private practice. So this is a practice where they don't have any there's no business case to be made for research to happen. And this is where most of the data sets reside. This is where patients go to seek care. So we have to figure out a way to overcome all of these challenges when we are thinking about developing the models, validating the models, or even deploying the models. And this is one of the reasons why we thought that having a workshop that focuses on resource-limited settings and starts to think about ways of overcoming the challenges, or even understanding the challenges, overcoming the challenges, and developing methods that are quite geared towards resource-limited settings, would it only benefit some of these settings, but actually benefit everybody. Because if you start to develop methods that work effectively with very little resources, then here in the West, we can doge it, for lack of a better word. We can start to use some of these methods and make them even more sustainable and more cost effective. So the first workshop we did was kind of timely. This kind of ran because MICCAI was coming for the first time to Africa. This happened last year in October, and we had the MICCAI Meets Africa workshop. It was organized by myself and a very few other like-minded people, including radiologists like Dr. Farouk Dako, and a long-time MICCAI and computer science experts like Tinashe from South Africa, and quite a few other people. We had sessions that were sort of topics that were skewed into three like call them topics or areas, one of a common or understanding those challenges and methods that can advance machine learning application, implementation, deployment in resource-limited settings, and obviously topics around driving ML innovations to improve care access in resource-limited settings. Had about 45 submissions, 9 talks, 12 abstracts. You can see the spread of the interest coming from the region and also people that are wanting to build models and apply them in the region. And you can see the segmentation, detection, even ultrasound, and that's a given because that's one of the most available methods out there, what people are interested in. And you can see the spread of where the papers came from. So a lot of the methods, a lot of the interests were not only from the low resource settings, it's obviously people are from all over the world wanting to understand and also build ML methods that can be applied, not just, like I said, in resource limited settings, but could also be transferred and applied or knowledge transferred and applied also in higher resource or high income areas. So this year, we're no longer going to Africa. So we thought that we go back to the original idea of what we wanted to do with the workshop, which is medical image computing for resource-constrained settings. We added this knowledge interchange, which I'm actually going to flip over to the website to talk a little bit about, because I think that's going to be of more interest to you guys. The call for papers is already closed. But what I wanted to touch on and make sure that you guys understand, because there's still an open call for the interchange, is that the topic areas are kind of similar to what I showed initially, which is just understanding some of the theoretical challenges that can be faced when machine learning methods are designed or to be implemented in resource-constrained settings, such as data scarcity or imbalanced representation, clinical outcome predictions that are focused on applications in some of these resource-constrained settings. Policy is actually quite important because there's a lot of policy gaps. And so trying to figure out how this machine learning methods that we're developing will work in areas where there's very little data protection or privacy or stuff like that is also of concern to the workshop. Like I mentioned, the call for papers is closed. But I want to swing over here, if you just give me 1 second, to the website. I don't know how much time I have to talk about the interchange, because I think that's going to be of more importance or interest to the group here. Let me just go over here, share screen again. Okay, so we have this, and again, the website is here. It's just very simple. It's event4waves.com/Mirasol. And we have this call for interchange, which is still open. The interchange is actually a session that we're going to run at the workshop for the first time this year. It's organized by students. It's a workshop. It's a session for students by students or for trainees by trainees, where we're trying to give trainees, especially those from some of these resource-constrained settings, so low middle-income countries, the ability to showcase the ideas. So you have groundbreaking ideas, but you don't sometimes have the resources. Resources include mentorship, because obviously there's lack of personnel. You don't have the computational infrastructure. You can take those ideas, put them into a short paper, essentially just describing a technical method, describing the motivation. It could be a research that you want to do. This could be a startup solution that you're thinking of, a product you're thinking of developing that has application of resource-constrained settings. And you can, you have to take that idea and put that in a 3-minute pitch. We're going to pick 3 of the papers and pitches that sort of captures promising methods, promising research ideas, promising startup solutions that just require a little bit of resources, mentorship, infrastructure, and allow them to come to the session at our workshop and just showcase that idea. You can call this Dragon Den meets 3MT. So 3-minute thesis / Dragon Den having a baby. This is what this is. And so the idea is to give students the ability to really learn how to take ideas from concept potentially to market, but having your ideas heard or heard by vendors. We're working with industry partners. We have PIs or researchers that will be in the panel, going through the ideas with you, and being able to provide you some feedback. The deadline to submit your 3MT thesis and short paper is August 1st. So this is still open. Just go to the website, go under the interchange section here in the website, click on submission, and what you have to do is just submit your short paper, your 3MT pitch. The short paper should still be the LNCS format. If you have any questions, just feel free to go to a contact us page and you can send us an email. We'll be able to help you sort that out. But I think this is something that the trainees in the room should be able to take advantage of. So I'm going to stop here. I think I'm over my 15 minutes and I'll turn it over if there's any questions.
Yeah, so thanks a lot, Uduna. So I think the Q&A actually coming a bit later. So feel free to actually share those links maybe in the Zoom chat, so that's how people can take a look. And then of course I'm going to update in our website as well. So no worry about it. And thank you. Thanks a lot, Uduna. And the next presenter is Alistair. Are you there?
Yeah, hi.
Hi, nice to meet you. So here's the will present about the Stockholm, the workshop in this year, for the MICCAI. And Professor Alistair Young is the chair of the Cardiovascular Data Analytics and AI at King's College London. And his research bridges machine learning, biomechanics, and statistical modeling to better understand heart function in cardiovascular disease. He leads the Cardiac Atlas project, providing the open cardiac imaging data and tools for large-scale heart analysis. And with over 190 journal publication and ties to industry, has helped translate the research into clinical products. So welcome, Alistair, and it's your time.
Yeah, thanks very much. So what I wanted to do is introduce the workshop from the point of view of what the workshop does and what the scope is. And it's a little bit different to what we've been seeing in the last couple of talks, because it's very application focused, I would say, in terms of modeling the heart or analyzing the heart. So STACOM stands for Statistical Atlases and Computational Modeling of the Heart. And it's been running since about 2010. So this year we're into our 16th year of this workshop. And really we decided that we needed a special workshop for heart analysis, because before STACOM, we were finding that there was a lot of things happening in heart disease analysis and image processing and biomechanics and electrical physiology and things like that, but they were kind of dispersed around in different sessions. And we thought it would be really good to get a community together to talk about heart-related issues in as it touches the MICCAI community. And so I think that that's been very successful. Every year we get about 50 participants to the regular workshop and many more to the challenges. And I think that reflects the fast development that's been happening in the cardiac analysis domain. You probably know that cardiac disease is still the #1 killer around the world, or it's up there in the first few. And it's interesting scientifically also because it's an organ that moves really fast. So it's hard to capture the dynamics of it. And it's got a lot of electrophysiology, it's got a lot of biomechanics, there's a lot of computation, which is kind of tractable. So we do know the underlying mathematics to a fair degree, and the problem that we have is trying to apply that to data that we get from imaging scans, let's say, or cardiology scans. So the workshop is to try and get a forum for researchers across a wide variety of disciplines, so engineers, physicists, mathematicians, clinicians, and we're trying to push the state of the art in terms of analysis of cardiac function and shape, statistical analysis, morphometrics, computational modeling, fluid dynamics, electrophysiology, biomechanics, and translation. And the ethos of StackOn is about data sharing. So we really encourage sharing of data, sharing of models, and benchmarking. So when we run workshops, we are typically running them in collaboration with a challenge, 1 or 2 challenges. And with the way that MICCAI has developed over the years, now those challenges are have a separate kind of pathway of scrutiny. So there's a lot of milestones and forms that you need to fill in for getting a challenge accepted by MICCAI now. And one of the things is it associated with a workshop? So if your challenge has to do with heart analysis, and typically there's 2 or 3 of these every year, we encourage them to join with us in the heart workshop and publish under a joint proceedings under LNCS. So this volume comes out every year, and it's a combination of the challenges and the regular papers. So this is the organizing committee, most of them anyway, from this year. You might recognize some faces, Esther from the RISE workshop here, and a few others. And these are some highlights from last year. So we award Best Oral Presentation and Best Poster Presentation. Best Oral last year was Gaussian Process Emulators for Few-Shot Segmentation in Cardiac MRI from Graz. And the best poster was a global control for local SO3 equivariant scale invariant vessel segmentation. So you can kind of see from that the range of the papers that we typically get, from vessels to heart and electrophysiology and mapping. And these were the 2 challenges from last year. There was one on atrial segmentation and one on reconstruction of images from raw data. And this year, the challenge will be a continuation of the Recon one for motion artifact reduction and efficient recon of 3D plus time images. And we tend to make these challenge data sets available to the community beyond the actual day of the challenge. So if you go to the Cardiac Atlas Project website, you can see previous challenges that were run at StackOn, and they're still open, a lot of them. So you can download the data and benchmark your methods against previous solutions that were published in the day. This is a shot of participants from last year in Marrakesh. So what I wanted to do is just draw your attention to the website here. So I think I'm still sharing, right? So you should be able to see the website called stackon.github.io, and there's a link there to the one in Daejeon, but there's also all these past ones as well. So you can get their link to the LNCS proceedings. You can get the links to the challenges, and this is an interesting resource for past workshops. And the Atlas project page is also interesting. It's just cardiacatlas.org. It has some data sets which you can download, and it's got some challenges here. So they go back for 15 years, and so these data sets are still available for people to work on. Okay, I might finish it there in the interest of time. So thanks very much, and happy to answer any questions.
Okay, thanks, Alistair. And then yeah, it's time for the Q&A, and then we're going to prioritize actually for MIRASOL the workshop. So is there any questions from the MIRASOL? I mean, if you raise your hands, I can make you maybe to speak up. There's a Julian, I think, or anyone else like wanted to ask about the MIRASOL workshop. Julian, are you still there? I just allow you to speak, so you can feel free to ask directly.
Julian, you may have to mute yourself to speak. Maybe you're still muted.
Okay. As to unmute.
Or he can write the question on the chat if he has problems, Julia.
I think all the question actually was visual, so
You might still be speaking but muted.
You're muted, Esther.
Okay.
Okay. I mean, yeah, I can, but I think there's nothing I can do. Like, okay, about the next gen interchange.
Oh yeah, okay. Okay, so the next interchange, are participants required to generate an idea or submit a research work? So I think because that's actually a great question. We've got a few emails about that. So I know some people missed the deadline for the workshop, and so you're trying to take your 8-page paper, make it a 4-page paper. That's not what it's about. It is about essentially you have an idea, you have a method, you just don't have the resources or the means to bring that idea into either a preliminary stage, so conference ready stage, or even a full paper stage. And so the idea here is that we will be able to, at least at the session, provide you with some amount of mentorship, meaning that you would get your really promising ideas, get like really good feedback, and potentially even get some resources to continue working on that idea, so that next year you can submit that to MIRASOL or to other MICCAI conferences, such as the ones presented here today. So that's the main idea. Like I said, this is more like a Dragon's Den. You're about to pitch an idea. You just don't have the means to do the research or the resources. So that's the main aim of the interchange. Yes, so if you go to MIRASOL, then you click on the interchange, you should be able to get more information about that. I think that's kind of it. Yeah. I think that answers that question, right?
Maybe about team name and then what kind of teams, like is forming the team for the.
Oh yes. So if you can be a team, you can be an individual, you can be a team, like a group of students, a group of early career people. It's fine. Team name doesn't matter. When you submit, you're going to submit to MIRASOL. So if you go back to this, if you click on that submission link, it will take you to the MIRASOL CMT page. So you're going to submit this like any other satellite event submission. You have your author list. If you have a team name, you can put that somewhere in the abstract. And it's again double blinded, just like any other MICCAI submission. So the 3-minute thesis video is going to accompany your paper. So that's where the unblinding might happen. But that's we want to make sure that at least people get the opportunity to try submitting the short paper as a typical MICCAI short paper. And that's fine if you add author names to your short paper. It's not an end all. But the submission is very identical to any other workshop through CMT.
How about the next question is, does it also require us to prepare MVP for submission or just theoretical pitch for now?
Yeah, you have to do the 3-minute video. Because we're trying, so the idea for this is also to kind of get you guys to learn how to pitch an idea. It's the elevator pitch. So it's part of the whole process of giving early career students or postdocs or even residents the opportunity to just kind of practice how to pitch an idea. So yes, the video is required, and we did put some resources and tips on how to prepare a 3-minute thesis, how to write a short paper. These short papers are like registered reports. I think in the computer world, you're not familiar with registered reports. In clinical practice, there is a lot of emphasis now on creating this registered report that's your idea, your methods, what you're going to do before you actually do the research. So you're trying to also see if that kind of makes its way into MICCAI, and obviously the way we do computer science. It might be nice for us to start to share ideas and our methods to get it have some sunlight before we start doing some of this research, especially if in a resource limited setting. So you don't waste too much time and effort going down the wrong path because you don't have too many resources. I think that kind of nails that question. If there's any more questions, send me an email. I'm happy to answer that.
Yeah, thanks a lot, Udna. So yeah, you have a schedule, right? So yeah.
Thank you.
Yeah, thank you. And any more questions regarding Stockholm or iMIMIC workshops? Okay. So hello, I have a question about explainability of models in health. And when explaining prediction from neural network in image, which technique are more recommended to use? Okay.
I can comment on that for Antonio. Hi, Antonio. So there's a ton. I have actually this image of a French supermarket with the yogurt, hallway, where basically there are so many techniques as yogurt when you go to the supermarket. So it's almost overwhelming, right? I think that here there are guidelines, so I can also, if you reach out, I can send you information and also some tips what's recommended. As I mentioned in my slides here, I think there's also an importance of what is the clinical goal that you want to achieve, or is just you are at the area of just, let's say, prototyping a new concept, and therefore maybe you're not at a, let's call it TRL 6-7 where you want a clinician to use the technology. But yeah, feel free to contact me. I will put my email there so I can hopefully help you with some details.
Yes, we're going to have slides. I mean, we're going to update in our website, and work together for the research paper. Yeah, of course, like it's in, I mean, either individual or like there's usually like co-authors and then submit together for the workshop. So I think that's totally fine. Okay. Any more questions about the workshop? The stuff? Okay. Okay, about the interability. Yeah. Interability, we could work with other architectural neural network that are more interpretable.
Hi, so yeah, I think also transformers, they have seemed to have a more interpretable. Here, we have to be careful that we tend to humanize models. So many times the attention map of a transformer, let's say an attention layer, it seems more interpretable because it looks better to a human, right? So there we also have to be careful about how do we interpret let's say the quality of the interpretability of the result. And so that's a kind of word of caution about the quality. And there's another one I see, collaboration. Yes, of course, there's always, it's good to catch maybe online or through in our conference and our venues. So happy to do that also offline. So maybe I don't know if you could see my email. Maybe the specific questions, we could take them offline.
Or maybe allow her to,
yeah, because I think this requires more time
or okay, there's less. Yeah.
Yeah, I guess the RISE organizers, they want to know more about like organizing a workshop and details of participations than the technicalities of a given approach. So I guess, correct me if I'm wrong, Esther, and Joy, if this is what you expect.
Yeah, exactly. So the idea was especially to show you some of the workshops that are available in MICCAI, as these are very good targets for next year if you're going to try to write a paper, and we have to try to select different ones, like in the current domain, and that interpretability, as well as more low resource settings. So yeah, as Mauricio mentioned, it's more about seeing what is there and yeah, get it inspired to maybe work or adapt your project that maybe could be suited for one of these workshops.
I would also add that just get involved, contact the organizers and say, if this is a topic that is close to my heart and I want to work on that, just get involved one way or the other. I think is a win-win situation for everyone.
Okay, then thanks a lot. I think this is we're gonna close the Q&A session, and then also it's a closing for day 2. And then yeah, we're looking forward to see you tomorrow, day 3. Or is there any comment like from Esther, like you wanted to say?
I just wanted to say, please check our website regularly, because Joy is making an amazing work trying to upload all the materials of the speakers, the slides, as well as the Zoom links. So if you keep checking, things are gonna come slowly. But I think, yeah, everything should be there by the end of the summer school. But if you, for instance, check, we already upload the slides from yesterday, and maybe later today or tomorrow, we're gonna try to upload the slides for today.
Okay, sounds good. Then see you guys tomorrow, the day 3.